Hello there, and welcome to Science for Sleep, where curiosity gets quiet, and the mysteries of the universe drift in at a pace gentle enough to settle your thoughts. Tonight, I'd like to bring you somewhere unusual, somewhere most people never even realise we're already moving through. Not a place filled with stars or glowing dust or colourful galaxies, but something far more understated. Something quieter. Something that, in its own strange way, is influencing the very path our entire region of the cosmos is taking. A place so empty that its emptiness alone is shifting us across space. It's a concept that sounds almost backward. How could nothing do anything at all? But as it turns out, the universe has a few surprises hidden in the dark stretches between galaxies. And one of those surprises is something called the local void. A vast region of deep cosmic emptiness that is quietly shaping our motion through the universe. And somehow, nobody really mentioned it. Before we wander too far into that idea, let me ask you something simple, something grounding. Where are you listening from tonight? Maybe you're settled in your bed, maybe you're curled up on a couch, maybe you're somewhere with the faint sound of cars outside or the soft hum of a fan. Wherever you are, what time is it right now in your little corner of the world? Even though we're all scattered across different places, different rooms, different moods and different clocks, we're sharing this moment together while gently exploring something incredibly large, something that spans hundreds of millions of light years. And all of it begins with the quiet pull of nothingness. If you find this kind of slow, thoughtful journey soothing or helpful as you unwind, I'd appreciate it if you'd like the video or maybe subscribe to the channel. It helps this quiet corner reach others who might need a gentle way to drift into the night. But for now, there's no rush. You're here, settling in, and the universe isn't going anywhere that quickly, at least not in a way you'd notice tonight. Let's begin by letting the mind settle into the idea that the universe around us is moving in ways that aren't immediately obvious. You and I and everything in our galaxy are drifting through space, not just because the Earth orbits the Sun, or the Sun orbits the centre of the Milky Way, but because the entire Milky Way itself is being nudged, guided, or perhaps influenced by something enormous. It's not the kind of influence that comes from a bright, powerful object, like a giant cluster of galaxies pulling us in with its massive gravity. Instead, it's the influence of a region that contains less than average, a neighbourhood noticeably empty compared to everywhere around it. And that emptiness is pushing us away. It's a strange idea, isn't it? We usually think of gravity as something that pulls things towards something else. If you drop a pen, it falls toward the Earth. If the Earth moves, it moves toward the Sun. If galaxies drift, they drift toward clusters of mass. But the story of the local void is a little different. It's the story of how the absence of matter can reshape the motion of entire galaxies, creating a sort of cosmic push. Not an active push, nothing like wind or pressure or force in the everyday sense, but a kind of drifting caused by imbalance. If one side of a galaxy has slightly more mass around it, and the other side has noticeably less, the galaxy ends up sliding toward the side with more mass. It's not that the emptiness is doing anything directly, it's that the rest of the universe is doing more. That quiet shift, that gentle slide, is the beginning of what scientists eventually traced back to the local void. But before anyone understood it, before the term even existed, astronomers noticed something odd. Our galaxy wasn't moving the way they expected. When scientists measured the motion of the Milky Way and the other galaxies in our immediate neighbourhood, something didn't add up. Everything was drifting in a particular direction, almost like a group of swimmers being carried by a slow, steady current. It wasn't dramatic, it wasn't chaotic, it was just there, a subtle drift through the cosmic waters. Eventually that drift raised questions. What was pulling us? Or was something else at play entirely? To make sense of that question, imagine standing in a large open field. The wind is soft, barely noticeable. If the air pressure on one side of you suddenly drops, you might not feel the drop directly, but the air on the opposite side might push in slightly more, nudging you without you ever feeling a breeze. Your movement would be subtle but real. That's not a perfect comparison to what happens in space, but it gives a sense of how imbalance can create motion without anything actively pushing. The local void is that region of lower pressure in the cosmic landscape, and the more massive structures around it are the places where that extra push comes from. But this isn't something you'd feel. Our planet, our solar system, even our entire galaxy, experiences this motion over scales of millions of years. To you, sitting or lying comfortably, the drift is calmer than a whisper. Yet in the wide, deep view of the cosmos, it shapes the paths of galaxies like a quiet tide. And before people understood what was happening, this tide puzzled astronomers. One direction, one consistent motion, one gentle but persistent flow. Something was causing it, but at first nobody could point to what. This wasn't the first cosmic mystery humans stumbled across, not even close. The universe is filled with motions we didn't expect. Galaxies orbit clusters. Clusters drift along filaments. Filaments form a cosmic web stretching across the observable universe. But when scientists first mapped the local region around the Milky Way, they expected a certain level of balance. Galaxies scattered in various directions, moving with no particular preference. But instead there was a pattern, a coherent motion almost like leaves being carried along by a faint river current. That motion hinted at something large and hidden, something shaping our trajectory, a place so empty it could shift entire galaxies. The term void can be a little misleading. When you think of a void, you might picture complete nothingness, a dark, empty hole. But cosmic voids are more subtle. They're not absolute emptiness. They're regions of the universe where there's significantly less matter than average. Fewer galaxies, fewer clusters, fewer stars. Think of them as enormous cosmic neighborhoods where hardly anyone lives. And the local void is one of those neighborhoods, stretching hundreds of millions of light years across. A vast expanse with very little inside it. Not nothing, just much less than elsewhere. Our galaxy happens to sit near the edge of this enormous underdense region. On one side, the universe is relatively populated, with galaxies forming groups and clusters. On the other side, there's this deep, prolonged dip in population. That imbalance creates the motion we're tracing tonight. But before scientists understood that, they had to understand something else. The motion of galaxies is complicated. They don't just drift because of one thing. There are many factors, including the overall expansion of the universe itself. Everything is spreading out, and galaxies are carried along with that expansion. But layered on top of that expansion are smaller motions, local quirks, gravitational nudges and pushes that shape how galaxies move relative to one another. Separating those motions, figuring out which part of a galaxy's motion comes from expansion and which part comes from local influences, is not a simple task. Imagine riding in a car that's moving down a highway while also shifting from lane to lane. If someone asked you how fast the car was drifting between lanes, you would have to subtract the highway speed from the total speed. The challenge astronomers face is similar. They have to separate the universe's expansion from the local drift to understand what's really happening. Once they did, they saw the motion clearly, and it pointed towards something unexpected. That subtle drift eventually directed their attention toward a region with remarkably few galaxies. It wasn't the influence of a massive cluster. It wasn't a giant gravitational well pulling everything inward. It was the opposite. It was the space where something wasn't. An absence that mattered. The local void. Even now, the idea that emptiness can shape our motion is counterintuitive. If you think about everyday life, emptiness never moves anything. A quiet room doesn't pull the furniture toward it. An empty shelf doesn't attract books. But space on cosmic scales behaves differently because gravity interacts with mass, and the lack of mass ends up creating relative motion that feels like a push. On one side of us, the universe is filled with galaxies. On the other side, it's nearly bare. So the galaxies around us drift ever so slightly away from that bare region. They drift toward the side with more matter. That drift is small when measured moment to moment, but enormous when measured across millions of years. Even the Milky Way participates in this motion. Our entire galaxy, with its hundreds of billions of stars, is sliding gently along the edge of the local void, carried by the same imbalance affecting all of the galaxies nearby. You, listening right now, are moving with it. Not in a way you'd ever notice, but in a way astronomers can measure with careful observations. And those observations grew more detailed as telescopes improved, revealing the quiet presence of the void. The local void isn't the only underdense region in the universe. There are many, some far larger. But this one is special because of how close it is to us. It sits right beside our local group of galaxies, shaping our motion in ways we only recently began to appreciate. For decades, scientists focused more on the places with lots of galaxies, because those places were brighter, easier to study, and more obviously influential. But as the cosmic map grew clearer, the emptiness became just as important. The universe is shaped not only by what exists, but by what doesn't. What makes this topic so intriguing is how quietly it remained hidden in plain sight. The local void stretches across an enormous portion of the sky, but because it contains so few bright things, it was easy to overlook. You can't see a lack of galaxies unless you're specifically looking for it. You can't point a telescope toward emptiness and immediately understand its influence. It takes careful mapping, patient analysis, and years of studying galaxy motion before the pattern reveals itself. The pattern of movement away from a region of nothingness. As we drift along this cosmic boundary, the local void continues to expand, not because it's actively growing, but because the universe around it is moving away from the emptiness. As galaxies flee its interior, the void becomes emptier still. It's a bit like an expanding bubble, but instead of expanding because something pushes outward, it expands because everything around it is leaving. That expansion deepens the contrast between the void and the region outside it, reinforcing the drift. And that drift affects us, quietly guiding the path of our galaxy group. All of this might feel like distant, abstract information, but it connects back to something simple. You, lying or sitting wherever you are part of this motion. Your entire existence, your home planet, your solar system, your galaxy, is being nudged along a slow, steady path shaped not by something present, but by something absent. A quiet influence from a region few people know exists. And that's the strange comfort of the local void. It doesn't demand attention. It doesn't glow. It doesn't roar. It doesn't produce dramatic events or wild cosmic behavior. It simply exists as a quiet place in the universe, a stretch of space where not much has happened for billions of years, and yet that calm region shapes our journey through the cosmos. It's a reminder that even emptiness has a role in the structure of the universe. Even the quietest spaces influence the loudest ones, and even the vast dark between galaxies has its own subtle story to tell. When astronomers began to look closely at the quiet shift of our own corner of the universe, they noticed something that didn't quite fit into the picture they expected. It wasn't just the Milky Way drifting gently through space. It wasn't just our nearest neighbour Andromeda sliding along its own trajectory. It wasn't even the smaller galaxies orbiting nearby. It was the entire group, the whole collection of galaxies that forms what scientists call the local group. This little cluster, which sounds modest on cosmic scales, is still a structure with more than 50 galaxies wrapped in and around it. Some are large and bright, others faint and irregular, many tiny and dim, but all of them participate in a shared journey. And when astronomers mapped where they were going, how fast they were moving and in what direction, they realized the pattern was too organized to be random. Everything seemed to be drifting in the same general direction, not just because of expansion, and not just because galaxies happen to move around one another. There was an added motion layered on top of everything else, a common drift shared across the local group. That consistent shift raised questions that took decades to fully understand, and it's part of why the local void became such an interesting piece of the puzzle. But before scientists got to the void itself, they had to unravel the motion of our small galactic neighbourhood. To make sense of what was going on, it helps to imagine the local group as a collection of islands floating on a calm but steadily moving ocean. The islands can shift relative to one another, tides can change their spacing, and currents can pull them in one direction or another. At first glance, each galaxy within the group seems to have its own little story, its own unique motion shaped by its mass, its nearby partners, and its internal structure. But when you step back and take a broader view, the pattern becomes clearer. The islands are not merely drifting randomly, they're being carried by a current. Astronomers first detected this current by studying something called the cosmic microwave background, the faint radiation left over from the early universe. This radiation fills the sky in every direction and is remarkably uniform, like a soft glow stretched across the entire cosmos. But if a galaxy cluster is moving in a particular direction, the radiation appears slightly warmer in the direction of motion and slightly cooler behind it. It's a subtle effect, but measurable. When scientists pointed their instruments toward the sky and looked for this temperature shift, they found it. The local group was indeed moving, not just due to the overall expansion of the universe, but because of an additional motion imprinted in the background radiation. This motion, called the peculiar velocity of the local group, was surprisingly large, not violent or chaotic, but significant enough that it couldn't be dismissed as a small quirk. It told researchers that something nearby, something substantial, was influencing the path of our entire galactic neighbourhood. At first, many believed it must be a gravitational pull from a large concentration of galaxies somewhere ahead of us. That idea made sense because mass attracts, and the universe is filled with clumps of mass in the form of galaxy clusters and superclusters, so the early explanations focused on finding a large, bright region toward which we might be falling. For a time, scientists thought they had found the answer in a region known as the Great Attractor, a massive concentration of galaxies located in a dense area of the sky. The Great Attractor certainly plays a role in shaping our motion. Its gravitational influence is real, and it explains part of the drift. But as astronomers improved their measurements and mapped the cosmos more carefully, they realized the Great Attractor wasn't the full story. The pull alone didn't explain everything, especially the subtle parts of the motion that still didn't quite fit. Something else had to be involved. Something not pulling, but indirectly pushing. This is where the local group's behaviour becomes especially interesting. If you picture the galaxies within the group clustered together like friends walking in the same direction, you can imagine that some of them might walk faster or slower, depending on how close they are to one another. But the overall direction of movement would likely be consistent, and that's exactly what astronomers observed. When they mapped the velocities of individual galaxies within the local group, they found a shared drift. Even the small dwarf galaxies far from the Milky Way's centre were participating. Their individual orbits might be messy, tilted or stretched, but the larger trend still rose above that noise. Understanding this shared motion required untangling many layers of movement. Earth's orbit around the Sun had to be accounted for. The Sun's motion around the centre of the Milky Way had to be subtracted. The Milky Way's motion inside the local group had to be carefully measured, and then, finally after all those corrections, the group's motion as a whole could be extracted. What remained was a clear shift in a specific direction, like a gentle current carrying an entire raft of galaxies quietly through the cosmos. That direction, interestingly enough, lined up with areas where the universe contained more mass on one side and less on the other. The side with more mass included the Great Attractor region and several other massive structures, and the side with less mass included something that received far less attention early on, an enormous empty region called the local void. This contrast between high-density and low-density regions is at the heart of cosmic motion. The galaxies in our local group weren't just being pulled by the massive clusters, they were also drifting away from the emptiness beside them. But before this interpretation became clear, scientists had to deeply examine the structure of the local group itself. The group includes some well-known galaxies such as the Milky Way, Andromeda, and the Triangulum Galaxy, along with dozens of small satellites orbiting the larger ones. Many of these satellites are faint and difficult to detect, but they're part of the system and they move with it. Understanding their motion helped refine the group's overall velocity. Take the Milky Way, for example. It has dozens of dwarf galaxies orbiting around it, each following its own path. Some of them move in elongated loops, others in relatively round orbits, some with trajectories that look almost chaotic. But when astronomers accounted for these internal motions, a shared drift still emerged. Andromeda too has its own family of satellites. The way those satellites moved helped confirm the broader pattern. Even galaxies that aren't gravitationally bound in a close sense still follow the overall streaming motion of the group. It's not a fast drift, not one you'd ever notice on human timescales, but over millions of years, it's enough to carry the entire group further away from the void and closer toward regions of higher density. What makes this especially fascinating is the scale involved. The local group spans several million light-years, yet this entire space is moving cohesively. Everything within it participates in the journey. The amount of coordination required for such a large structure to move in unison is remarkable. On smaller scales, chaos dominates. Stars orbit chaotically within galaxies. Gas clouds swirl unpredictably. Dwarf galaxies tumble around their larger neighbours. Yet when you zoom out far enough, the local region moves like a single unit. It's a reminder of how structured cosmic motion can be when viewed from a broad perspective. As scientists studied this drift more closely, they realized the speed of the local group's peculiar motion is greater than expected from the gravitational pull of nearby structures alone. It was as though the group was trying to move away from something behind it. That idea seemed unusual at first because gravity doesn't push, but imbalances can create motion that mimics a push. If one side of the local group contains fewer galaxies and less mass, then gravitationally speaking, the other side does more of the work in shaping motion. The galaxies drift toward the side with more mass simply because that's where the gravitational pull is strongest. But the interesting part is what lies in the direction opposite our motion. That opposite direction is where the local void resides. The emptiness behind us isn't pushing in any physical sense, but the lower density creates an imbalance that leads to motion away from it. This became evident once researchers mapped galaxy density in all directions. The void appeared like a deep dip in the cosmic landscape, while the other side rose like a series of hills made of galaxy clusters. The local group slides toward the hills because there's nothing equivalent behind us to balance the pull. To appreciate how scientists discovered this, it's useful to understand how galaxies serve as markers. Galaxies move with the expansion of the universe, carrying along the space around them, but their additional motions on top of that expansion can reveal hidden structures. If galaxies around us appear to be drifting in a certain direction, that drift hints at the distribution of matter around them. When astronomers plotted these motions in three-dimensional maps, the local group's shared drift stood out clearly. The pattern pointed away from the void and toward regions filled with clusters and superclusters. One of the most compelling aspects of this research was the discovery that even galaxies beyond the local group, in the surrounding regions, showed similar motion. These galaxies were not gravitationally bound to us. They had no direct relationship to our group, yet they too felt the influence of the imbalance between the void and the massive structures. That meant the effect wasn't confined to our cluster, but part of a much larger flow in the neighbourhood of the universe. This broader flow reinforced the idea that the local void plays a significant role in shaping local cosmic motion. Another important detail came from studying how galaxies at the boundary of the void behaved. Those galaxies appeared to be receding from the void at a faster rate than expected from the expansion of the universe alone. They were moving away in a way that suggested the void was growing, or at least becoming emptier as galaxies continued to drift outward. This behaviour matched predictions from models of cosmic structure formation. Voids grow not by creating outward pressure, but by being regions where matter is sparse, so the surrounding matter moves away more easily. That movement causes the void to become even emptier with time. With all of this evidence, the picture of the local group's motion became clearer. Its strange drift isn't the result of a single explanation. It's the result of several influences layered together. The gravitational pull from large structures ahead, the imbalance caused by the emptiness behind, and the shaping of motion through the uneven distribution of mass on cosmic scales. The local group is navigating a landscape where hills and valleys of galaxy density guide its direction. Now, as you listen, it's helpful to keep in mind that these motions are incredibly slow on human scales. The local group drifts at hundreds of kilometers per second, which sounds fast. But when you place that speed against the vast distances in the universe, the motion becomes gentle. It's not a rush. It's not a tug you could feel. It's a patient, steady glide across unimaginable distances. If you could watch it from outside time, if you could stretch human experience across millions of years, you would see the group shift smoothly away from the emptiness, following the contours of the cosmic landscape. But from our lived perspective, everything feels still. Our world remains solid beneath us, and the stars overhead appear steady. Still, the motion matters. It reveals the structure of the universe. It shows how galaxies cluster, how voids form, how filaments stretch across space. It tells us that the universe isn't uniform. It's a patchwork of crowded places and empty ones, dense regions and sparse ones, bright clusters and dark voids, and our small group of galaxies moves according to the distribution of that cosmic terrain. As scientists continue to trace the motion of the local group, the pattern that emerged didn't feel like an isolated quirk or an accident of positioning. It felt more like part of a broader, gentle flow that stretched well beyond our collection of galaxies. To understand it, researchers had to look farther than our immediate neighbourhood, past the familiar spirals and scattered dwarfs that orbit the Milky Way and Andromeda. They needed to examine how the surrounding galaxies moved, not just individually, but together. And when they did, the view became even more intriguing. The local group wasn't drifting alone. It was part of a larger stream of motion, almost like a soft current flowing through a wide cosmic sea. This current wasn't something you could see by looking through a telescope. It wasn't visible in the shape of galaxies, or in the glow of their stars, or in the arrangement of gas and dust. Instead, it revealed itself through precise measurements, through tracking how light stretched or compressed as galaxies moved toward or away from us. Those small changes in light, when gathered across enough galaxies, created a map of motion, and that map showed that many galaxies near us were drifting in roughly the same direction. They weren't being pulled sharply, and they weren't moving chaotically. They were gliding. One of the surprising early hints came from galaxies on the outskirts of the local void. These galaxies, positioned at the boundary between the emptiness and the more crowded regions, showed a distinct motion. They were shifting away from the void at a pace that couldn't be explained by the normal expansion of the universe alone. It wasn't dramatic, but it was measurable. The data showed a gradual acceleration away from the emptiness. That acceleration suggested that something about the void's low density was influencing the nearby galaxies. This wasn't entirely unexpected. Computer simulations of cosmic structure formation had predicted that voids should grow as the surrounding galaxies drift outward. But to see it happening so clearly in our own cosmic neighbourhood was striking. It meant the local group wasn't simply moving toward dense regions. It was also moving away from an enormous underdense one. And the interplay of these two influences created the peculiar drift that astronomers were trying to understand. To picture this drift, imagine standing at the edge of a vast, gently sloping valley. On one side of you, the ground rises toward a series of hills. On the other, it dips into a wide, quiet lowland. If you dropped a ball right at the boundary between the valley and the hills, it wouldn't simply roll toward the hills because they were higher. It would roll because the slope beneath it guided its path. In the same way, the galaxies near the local void aren't being actively pulled by the void. They're moving because the landscape of matter around them slopes upward toward denser regions. The void is the lowland, and the mass on the other side is the rising terrain. But there was something else that made the drift especially interesting. The direction of motion wasn't exactly aligned with the biggest nearby structures. It wasn't directly toward the great attractor. It wasn't perfectly toward any single massive cluster. Instead, the motion appeared to be a combination of influences. The local group was drifting toward one area, but also subtly angled away from another. When astronomers plotted this on the sky, the vectors, the little arrows showing direction and speed, revealed a pattern that didn't point to a single explanation. It had layers. One layer came from the large-scale structure of the universe. On the bigger scales, galaxies flow along the filaments of the cosmic web. These filaments act like pathways shaped by gravity, connecting clusters and spanning vast distances. The local group sits on one of these filaments, and its motion is partly guided by that structure. But another layer came from the nearby mass distribution, the clusters and groups that exert strong gravitational influence. And then there was the layer that came from the void. It took a lot of work to separate these layers. Researchers had to gather redshift data from thousands of galaxies, build detailed maps of mass density in the local universe, and compare that data to predictions from simulations. They had to correct for bias in observations, fill in the regions of the sky obscured by the Milky Way's dust, and cross-check patterns using different methods. Each piece of the puzzle helped refine the picture. What remained, after all the analysis, was a distinct drift, a peculiar motion shaped by both presence and absence. This drift is easiest to understand when you look at the galaxies just outside the local group. These galaxies, which are near but not part of the group, show similar patterns of motion. Some of them lie closer to the void and move away from it faster. Others lie closer to the denser regions and pull more strongly toward them. The interplay between these tendencies forms a larger flow that extends across tens of millions of light years. It's as if the entire neighborhood is influenced by a gentle slope in the cosmic terrain, guiding everything toward the same approximate direction. One of the clearest examples comes from studying the motions of galaxies near the boundary of a structure called the local sheet. The local sheet is a flattened arrangement of galaxies, including the Milky Way and several others, lying along a plane. This plane is not a physical barrier, but a region where galaxy motions are particularly coherent. The galaxies in this sheet move together more smoothly than those outside of it, almost like a raft rather than separate islands. When astronomers studied how this sheet moved relative to the surrounding structures, the pattern was remarkably consistent with the drift away from the local void. The local sheet itself appears to be sliding outward, away from the void and toward regions of higher density, not rapidly, but steadily. That steady movement explains part of what the local group is doing. The group isn't drifting alone, it's part of this sheet, and the sheet is responding to the cosmic terrain around it. This also helps explain why the drift feels peculiar. It's not simply a matter of falling toward a massive cluster. It's the combined result of following the path carved out by the sheet, moving away from the void, and responding to the pull of denser regions. What makes this even more interesting is that some galaxies on the far side of the void move in nearly the opposite direction. They're not part of the same flows as the local group because they sit in a different part of the cosmic landscape. Their motion is shaped by their own local environment. The fact that galaxies around the void move in different directions depending on their positions helps confirm that the void plays a significant role. It's not that everything is being pulled to a single point. It's that everything is sliding away from the emptiness and toward the places where mass is concentrated. This drift affects not only the galaxies at the boundary, but the void itself. As the surrounding matter moves outward, the void expands. Its edges stretch farther into space, and the region inside becomes even more underdense. The void deepens simply because galaxies continue to move away from it. This slow growth isn't a dramatic event. It's not something that happens in a burst or a collapse. It's a natural, gradual outcome of how gravity shapes the universe over billions of years, and the local group is part of that process, carried along by the surrounding motion. To appreciate the scale of this drift, consider that the local group moves at over 600 kilometers per second relative to the cosmic microwave background. That number sounds enormous. It's far faster than any object moves in everyday experience. It's faster than any spacecraft humans have ever built. But when placed in the context of cosmic distances, it becomes relatively gentle. At that speed, it would take over 1 billion years to cross the local void, and even longer to reach the nearest dense region shaping its motion. The drift is steady but unhurried, shaped by forces acting across unimaginably vast distances. Another part of what makes this motion peculiar is that it isn't entirely aligned with the visible galaxies. If you look in the direction the local group is moving, you won't see a single bright cluster sitting right in front of us. Instead, you'll see a combination of structures spread across a wide area. The pull comes from multiple sources, each contributing a part of the overall motion. Meanwhile, the void behind us creates a region of low gravitational influence, which enhances the effect of the forces in front. This combination makes the drift feel more like a push from behind and a pull from ahead, even though gravity itself only pulls. As researchers mapped these influences, they developed a clearer sense of how the local group fits into the broader patterns of cosmic motion. They saw that our drift is not a random flow, but part of the hierarchical way the universe organizes itself. On the larger scales, the cosmic web dictates the paths galaxies follow. On smaller scales, local mass concentrations tug on their neighbors. On even smaller scales, voids shape how galaxies move by providing regions where gravitational pull is weaker. Each scale adds its own flavor to the motion, and together they create the peculiar drift we observe. Perhaps one of the most meaningful aspects of this is the reminder that our place in the universe is dynamic. We often imagine galaxies sitting still in space, glowing quietly with their stars, but their paths are shaped by the landscape around them, just as rivers follow the contour of land and air currents follow temperature differences. The local group's drift through the cosmic sea is a reflection of that landscape. It's a sign that even at the larger scales the universe has structure. It has gradients and paths, slopes and valleys, dense patches and sparse ones, and the galaxies follow those contours without needing any dramatic events or sudden motions. This perspective also helps scientists study cosmic evolution. By understanding how galaxies move now, researchers can infer how structures formed in the past. They can simulate how the void grew, how the filaments stretched, how the clusters gathered mass. The peculiar drift becomes a clue about the history of our region. It tells them that the local void has likely been empty for a very long time, and that the dense structures on the other side have grown over billions of years. The drift isn't just a motion happening today, it's the visible result of a story that began far in the past and continues into the future. The drift also connects directly to the next step in understanding the local universe, the discovery of the more complex cosmic tug, the layered gravitational influences that sit ahead of us. Before that can make sense, though, the drift itself must be understood as a natural response to the shape of the cosmic terrain. That terrain guides everything, including our own journey. And as we continue moving through it, the quiet influence of the void and the pull from the denser regions together create the motion we interpret as peculiar. The local group isn't alone in this. Other galaxy groups across the universe also drift relative to the cosmic microwave background. Each one follows its own path shaped by the mass distribution around it. But because the local void lies so close to us, its influence is especially noticeable. It plays a significant role in shaping the path of our small cluster, and as the void expands, that influence becomes even clearer. The more astronomers studied this, the more they realized that understanding the drift required understanding both ends of the motion, the side with the emptiness and the side with the mass. The motion arises not from one or the other, but from the contrast between them. As astronomers pieced together the unusual motion of our galaxy group, they reached a point where the simple explanations no longer held. The idea that everything was drifting because of the local void on one side helped clarify part of the motion, but not all of it. The drift had layers, and one of the strongest layers pointed towards something else, something large enough to influence thousands of galaxies, not just ours. Before the local void became widely recognized as a major factor, scientists spent years studying this other influence, an immense region that seemed to pull on galaxies from far across the cosmic landscape. And it was in the search for this influence that the idea of a great cosmic tug first emerged. The discovery didn't happen all at once. It came gradually, through decades of observations, arguments, revisions, and the slow accumulation of data from telescopes around the world. To understand how astronomers reached that point, it helps to step briefly into the mindset they had when these measurements were first being collected. Back then, the universe was already known to be expanding. Galaxies were moving away from each other on average, carried by the growth of space itself. But on top of that expansion, many galaxies exhibited additional motions, peculiar velocities, that didn't fit neatly into the expected pattern. These velocities suggested the presence of large structures influencing motion in ways that were not yet fully mapped. One of the largest clues came from something called the dipole anisotropy in the cosmic microwave background. This dipole pattern showed that the local group was not only moving because of the expansion, but had an extra velocity layered on top of it. The direction and magnitude of that extra velocity pointed toward a certain region of the sky. That region didn't appear dramatically different to the naked eye. It wasn't brighter. It didn't contain anything obviously unusual. But the motion pointed toward it again and again. This raised the possibility that the galaxies around us were responding to a great concentration of mass in that direction. The early interpretation of this pattern was straightforward. If galaxies were moving toward a certain area, it made sense to assume there was a dense structure pulling them. That idea fit well with gravity, which always pulls and never pushes. So the search focused on identifying the structures that lay in the direction of the motion, on the assumption that those structures must be responsible. Several candidates appeared. Some were nearby clusters, others were massive superclusters lying farther away. But none of them alone could account for the entire magnitude of the motion. It was clear that something larger was contributing. This search led researchers into a region of the sky that had not been well mapped at the time. A large portion of the sky is partially obscured by the Milky Way's disk, filled with dust and gas that block the light from distant galaxies. This region, called the zone of avoidance, hides a great deal of the universe behind it. For decades, astronomers suspected that some of the missing clues might lie there, hidden behind our own galaxy's structure. But penetrating the zone of avoidance required radio and infrared observations, which were not widely available in the early stages of the investigation. As new observational tools became available, scientists started to peer more effectively through the dust. Radio telescopes helped detect the signature of hydrogen gas in distant galaxies, bypassing the blockage from the Milky Way. Infrared telescopes detected the glow of stars obscured by dust in visible wavelengths. As these tools improved, a clearer picture of the hidden region emerged. Behind the dense band of our galaxy lay an enormous concentration of galaxies, spread across hundreds of millions of light years. This structure, known today as part of the Norma cluster and its surrounding region, was one of the first major hints that a significant gravitational force was shaping the motion of galaxies like ours. Over time, as more data accumulated, scientists began to call this influence the Great Attractor. The name wasn't meant to imply anything mystical. It simply reflected the idea that this region contained an unusually large amount of mass, enough to pull galaxies toward it over vast distances. And for many years, the Great Attractor was seen as the main explanation for the peculiar motion of the local group. But that explanation didn't entirely resolve the puzzle. Even accounting for the Great Attractor's mass, the magnitude of the observed drift seemed slightly too strong. The gravitational pull in that direction could explain part of the motion, but something else was still needed. Some researchers suggested that a larger structure behind the Great Attractor, another massive supercluster called the Shapley concentration, might be contributing. The Shapley region contains some of the densest known clusters of galaxies in the nearby universe, far larger and heavier than the Great Attractor itself. Its influence stretches across impressive distances, and it was a compelling candidate for explaining the remainder of the motion. But even this didn't fully solve the problem. The motion of the local group continued to show signs of being influenced by something behind it, as well as something ahead of it. The values didn't quite match cosmological models unless there was also a deficit of mass behind the local group. This was where the concept of the local void finally began to enter the picture. The Great Attractor and the Shapley concentration were pulling from one side, while the void created an imbalance on the other. The motion wasn't due to a single force. It was the result of a combination of influences that together created what we now call the Great Cosmic Tug. The interesting part is that astronomers had essentially discovered this tug before they knew what all its components were. They recognised the motion first. The explanation came later. And in that sense, the discovery was similar to many others in science. A pattern appears in observations long before its cause becomes clear. Scientists follow the pattern, gather more data, refine their measurements, and search for an explanation until the pieces start to fall into place. The discovery of the cosmic tug is a good example of how that process unfolds. To understand why the tug felt so strong, researchers had to look at both the dense structures ahead of us and the underdense region behind us. The Great Attractor and the Shapley supercluster contributed a strong pull. The local void contributed a push-like effect created by the relative lack of gravitational pull in its direction. Together, these influences created a motion much larger than the contributions of any one structure alone. Mapping this tug was a major challenge. It required careful measurement of thousands of galaxies, many of which had faint signals. It required reducing observational errors and correcting for biases. It required detailed models of large-scale structures and their evolution over cosmic time, and it required a better understanding of the local environment around the Milky Way. One of the important developments in this process came with surveys that mapped galaxy distances more precisely, not just their redshifts. Redshift tells astronomers how fast a galaxy is receding due to the expansion of the universe, but distance measurements are needed to separate expansion from peculiar motion. Several techniques were developed to measure distances, including standard candles such as Cepheid variables and Type-A supernovae, surface brightness fluctuations, and Tully-Fisher relationships for spiral galaxies. Each technique provided a different type of clue, and together they built a more complete map of the local universe. As the data grew, the shape of the cosmic tug became clearer. It wasn't a single straight-line motion toward one spot in the sky. It was a gently curved flow influenced by multiple mass concentrations and shaped by the presence of the local void. The tug pulled in one direction, while the void allowed galaxies to slide away in another. The combination produced the motion measured in the cosmic microwave background. And the closer astronomers looked, the more they realized that the tug was not an isolated phenomenon. It was part of a larger flow that extended across a region spanning hundreds of millions of light years. Another important piece of the discovery involved studying how galaxies beyond the local group reacted to the same influences. If those galaxies showed similar patterns of motion, it would confirm that the forces shaping our drift were not unique to us. Indeed, galaxies well beyond the local group also exhibited motion toward the same broad region and away from the same underdense area. This similarity strengthened the interpretation that the Great Cosmic Tug was a collective effect shaped by large-scale structures, not just a peculiarity of our specific group. The more astronomers studied this, the more they realized that our part of the universe is not a static environment. It's dynamic. It's shaped by complex interactions between dense regions and voids, and our galaxy cluster is only one participant in a much larger pattern. The tug extends across multiple layers of cosmic structure, and our drift is just one segment of a long, gentle flow that threads through the universe. This understanding helped reframe what the local group's motion means. Instead of seeing it as a simple fall toward a massive cluster, researchers began to see it as a response to the entire surrounding density field. The local group is following a path carved by the distribution of matter and its absence. That path leads away from the void and toward the dense regions, creating a layered motion that reflects the shape of the cosmic web. As new surveys expanded the map of the universe even further, scientists could place the local group's motion into an even broader context. They could see how the great cosmic tug connected to the distribution of superclusters and filaments. They could trace how the motion responded to regions of varying density, and they could identify other voids and dense clusters that contributed smaller influences to the overall flow. The tug itself isn't a literal force, it's a shorthand for describing the combined gravitational effects of the surrounding mass distribution and the relative emptiness of the local void. It's the result of the universe's uneven structure. The galaxies follow the path carved by that unevenness, moving in ways that reveal the unseen contours of space. And that brings us to an important point. The discovery of the cosmic tug wasn't really about finding a single object, it was about understanding the terrain. By studying the drift of galaxies, astronomers were mapping the shape of the universe. They were identifying where mass had gathered over billions of years and where it had not. They were learning how voids formed, how filaments stretched across space, and how superclusters shape the gravitational landscape. The tug was simply the most noticeable signpost pointing toward that deeper structure. When astronomers first began mapping the large-scale structure of the universe, their attention naturally focused on the bright places. You can see why. Clusters filled with thousands of galaxies shine clearly through telescopes. Filaments stretching between those clusters become visible once enough data accumulates. Even smaller galaxy groups like ours stand out against the darkness, each knot of stars marking another location where matter is gathered. But the more the maps expanded, the more researchers realized that most of the universe isn't made of bright structures at all. Instead, enormous regions appeared that contained very little. These weren't pockets of exotic material or strange phenomena. They were simply underpopulated, sparse, vast, and these regions came to be known as voids. A void is not a hole in space. It's not an empty bubble in the sense of absolute nothingness. Even the emptiest void contains some matter. A few galaxies here and there, stray clouds of hydrogen, scattered stars, and the quiet hum of dark matter spread thinly through the region. But compared to the average density of the universe, a void contains much less. In some cases, these regions have only about 1/10 of the typical number of galaxies. In the most extreme voids, there may be barely any visible galaxies at all. Understanding what a void truly is requires adjusting how we think about empty space. On human scales, emptiness is something we barely notice. An empty field doesn't pull you toward it or push you away. A room with nothing in it doesn't influence how you walk through it. But on cosmic scales, emptiness becomes meaningful because gravity is shaped by how matter is distributed, not just by where matter is. When a region has significantly less matter than the surrounding space, it changes the gravitational landscape. It's like a valley in a terrain that would otherwise be fairly even. Matter doesn't rush into the void all at once. Instead, over billions of years, galaxies gradually move away from underdense regions, not because something inside the void is pushing them outward, but because the pull on the outside is stronger. To picture how a void forms, imagine the early universe. After the Big Bang, the universe was almost perfectly uniform. Tiny differences in density existed, just small fluctuations, but over time those differences grew. Regions with slightly more matter pulled in even more, becoming denser and eventually forming galaxies, clusters and filaments. Meanwhile, regions with slightly less matter became sparser. Their lower density meant they couldn't pull in matter as effectively, so the surrounding areas grew denser while the emptier spots grew even more empty. Over billions of years, these differences amplified. Dense regions became richer in structure. Sparse regions became voids. The patterns we see today, with their intricate web-like arrangement, are the result of that long process. That's why voids are not unusual. They're a natural part of how the universe evolves. They appear everywhere in large-scale surveys. They vary in size, shape, and depth, but all of them represent places where matter simply didn't gather as strongly. And because matter gathers elsewhere, the galaxies that form in dense regions gradually move away from the underdense ones. This movement causes the voids to grow over time, not because matter escapes violently or collapses inward, but because galaxies follow gravitational gradients that guide them toward denser environments. One of the striking features of voids is their shape. Unlike neat spheres, voids can be elongated, irregular, or distorted because the surrounding structures aren't uniform either. They form where density dips, but that dip doesn't have to be perfectly round. Over time, smaller voids merge into larger ones, creating sprawling underdense regions that stretch across tens or even hundreds of millions of light years. Each void is unique, shaped by how the surrounding filaments and clusters developed. Some are isolated, others connect to neighbouring voids, forming a kind of underpopulated network between the bright areas of the cosmic web. The local void, which sits right beside our own small group of galaxies, is one such region. But before astronomers recognised its significance, they had to understand what voids actually do. At first glance, it might seem like voids would have little influence. They don't contain many galaxies, their mass is low, they lack dramatic features like the dense clusters that create powerful gravitational attractions. But the absence of mass creates its own kind of influence. A void doesn't pull, but it doesn't need to. The stronger pull from denser regions effectively pulls galaxies away from the void. The result is motion that appears as though the void is pushing, even though nothing inside is exerting a force. This idea can be confusing, but it becomes clearer with an analogy. Imagine two people standing on a large open field. One person is pulling on a rope tied around your waist. The other is simply standing still. If the puller moves backward, you move toward them. But in the process, you're also moving away from the person standing still. That still person never pushed you. They didn't apply any force. You simply ended up farther from them because the pull on the other side was stronger. That's roughly how voids work. They don't push. They simply lack the pull that denser regions provide. When astronomers began measuring the peculiar motions of galaxies around the local void, they noticed this same effect. Galaxies on the boundary were moving away from the void faster than expected. The rate could not be explained by cosmic expansion alone. It had to come from the imbalance between the mass-rich regions on one side and the emptiness of the void on the other. The galaxies weren't accelerating because of something inside the void. They were responding to the strength of the pull outside it. The entire system becomes easier to grasp when you look at the cosmic web as a whole. Filaments, clusters, and groups form the bright nodes of the web. Voids fill the spaces between those nodes. The motion of galaxies flows along this web guided by its structure. Matter moves toward dense areas because gravity draws it in. As a result, the spaces between those dense areas become more pronounced. Voids grow because everything surrounding them moves outward. The local void in particular shows noticeable expansion because the galaxies near it, including those in the local sheet, drift away from it over time. One of the most interesting aspects of voids is how they influence the shape of nearby structures. The local sheet, for example, is a relatively flat arrangement of galaxies that includes the Milky Way and many others. This sheet is positioned along the edge of the local void. The void's presence creates a kind of gravitational imbalance that keeps the sheet unusually thin. The galaxies within the sheet follow a smoother motion than those outside it. As the void expanded, it shaped the region beside it, stretching the sheet in one direction and reinforcing its flatness. This helps explain why our galaxies lie within such a defined plane, rather than scattered randomly in 3 dimensions. Voids also give astronomers a way to study the universe's evolution. Because voids have such low density, they expand at slightly different rates than denser regions. By measuring the size, shape, and behaviour of voids, scientists can test models of cosmic growth, dark matter distribution, and the overall structure of space. Voids act as sensitive indicators of how the universe behaves on large scales. They reveal how matter has moved over billions of years and how gravity has shaped the cosmic web. In some ways, their emptiness makes them easier to interpret because fewer complicated interactions occur inside them. Clusters are filled with messy dynamics, collisions, mergers, hot gas, and complex gravitational fields. Voids are simpler. Their growth reflects the behavior of the surrounding structures more clearly. Another important point is that voids are not static. They evolve. As galaxies move away, the void becomes emptier. As neighbouring voids merge, a larger void takes shape. The boundaries shift as matter redistributes. Even though these changes occur over vast timescales, they help astronomers track the flow of the universe. The local void, for instance, appears to be growing as galaxies continue to drift away from its centre. This slow expansion contributes to the overall motion of the local sheet and the local group, shaping our path through space. The void's influence doesn't end at its boundary. It affects the flow of galaxies even beyond the immediate region. The peculiar velocities of galaxies tens of millions of light-years away still reflect the terrain shaped by the local void. This influence becomes part of the larger cosmic tug that guides our motion toward regions of higher density. The void creates an imbalance in the gravitational field, and that imbalance plays a role in the larger flow we observe. Understanding voids also helps explain why galaxies cluster where they do. In the early universe, slight differences in density set the stage for everything that followed. Dense spots grew denser, sparse spots became voids. Over time, matter naturally migrated toward the denser regions. This migration means voids become less populated as the universe ages. They act almost like sinks, not in the sense of pulling things in, but in the sense that nothing stays near them for long. Matter gravitates toward the areas where more matter already resides, reinforcing the structure of the cosmic web. And yet, voids are not perfectly empty. Some galaxies do live inside them. These galaxies tend to be small, faint and isolated. They evolve differently from galaxies in dense regions because they have fewer interactions, fewer mergers, and less gravitational influence from neighbours. Studying these void galaxies helps astronomers understand how environment shapes galaxy evolution. In dense regions, galaxies collide and merge frequently, leading to rapid changes. In voids, galaxies evolve quietly, influenced mostly by their own internal processes. Their solitude makes them interesting test cases for understanding star formation, gas dynamics, and the role of environment in shaping galaxies. Despite their differences, all voids share the same basic characteristic. They have lower density than their surroundings. This simple fact creates a ripple effect across the cosmic landscape. The presence of voids influences how clusters form, how filaments stretch, and how galaxy groups move. The local void, being so close to us, plays a particularly noticeable role in our region. But the idea of a void's influence wasn't immediately obvious. For many years, astronomers focused primarily on the places where matter was concentrated. The bright clusters were easier to study. They were visible, measurable, and dramatic. Voids were overlooked simply because they were quiet. They lacked features that drew attention. It took carefully mapping galaxy motions to realize that the quiet regions were just as important as the bright ones. Without voids, the universe's structure would look very different. As the maps improved, the edges of the local void became clearer. Researchers could see which galaxies formed the boundaries and how their motions differed from those elsewhere. They could measure how those galaxies drifted away from the void and how that drift changed over time. This data helped confirm that the void was actively influencing the local environment. It wasn't simply a passive patch of emptiness. It was part of the terrain that shaped the motion of the local group. To fully grasp the significance of the local void, one must consider its size. The void spans a large region, extending across tens of millions of light-years. Its centre is extremely sparse. The galaxies near its boundary mark the transition between the emptiness and the denser regions around it. Our own galaxy group sits just outside that boundary, close enough to feel the effects, but not so close as to be inside the void itself. This positioning means that our entire group drifts away from the void as it expands. The movement is slow and steady, shaped by the contrast between the void and the mass-rich regions that lie in the opposite direction. This gentle drift, influenced by both presence and absence, forms part of the layered motion that scientists refer to when they describe the great cosmic tug. The local void creates one part of the imbalance that shapes our path. The dense clusters ahead create the other. Together, these influences explain much of the peculiar drift observed in the local group and the surrounding galaxies. When astronomers finally turned their attention to the large empty region beside our galaxy group, they realized they had spent decades looking past something enormous simply because it wasn't bright enough to draw the eye. The local void didn't announce itself with clusters of galaxies or dramatic structures. It didn't glow or produce events that could be spotted easily from telescopes. It simply existed quietly, stretching across a region so empty that it took careful mapping and gradual analysis to recognize how large it really was. And once its presence became clear, the realization followed that it wasn't only a passive feature of the cosmic landscape. It was influencing the motion of our galaxy group in meaningful ways. The local void sits adjacent to the part of the universe that contains the Milky Way, the Andromeda Galaxy, and the rest of the galaxies in the local group. To understand what makes it remarkable, imagine looking at a map of your neighborhood where certain streets are filled with houses and activity, while a large block nearby contains almost nothing at all. At a casual glance, you might overlook the emptiness because your attention tends to fix on the places that stand out. Something similar happened in astronomy. The bright regions full of galaxies always attracted more study, leaving the emptier ones largely ignored, until clearer maps showed how they shape the space around them. The local void is a large, irregular region with significantly fewer galaxies than the cosmic average. It spans more than 100 million light-years in certain directions, though defining its exact boundaries is difficult because voids blend gradually into the structures beside them. Unlike a wall or border, the edge of a void is simply the place where galaxies become noticeably more common. This gradual transition makes it challenging to map precisely, but it also reveals how voids function. They don't have rigid edges. They're part of a continuous landscape shaped by the distribution of matter. One of the early clues about the local void came from the motion of galaxies in a flattened structure known as the local sheet. The local sheet includes the Milky Way, Andromeda, and many others arranged in a broad planar configuration. Galaxies within this sheet move more coherently than the galaxies above or below it. This coherence hinted that something was shaping their motion collectively, something that lay alongside the sheet rather than scattered evenly around it. When astronomers examined the motion of galaxies near one end of the sheet, they noticed that these galaxies were drifting away from a particular region faster than expected. That region was the local void. The position of the local sheet relative to the void created a kind of gravitational imbalance. On the far side of the sheet lay structures filled with clusters, groups, and filaments of galaxies, regions with plenty of mass. On the void side, space contained much less. This difference meant that the gravitational pull from the dense areas was greater, drawing the sheet toward them. The galaxies weren't being pushed by the void. They were moving because the pull from the opposite direction dominated. This effect becomes noticeable only when looking at many galaxies at once, because the distances involved are enormous, and the drift is subtle when viewed from the scale of a single star or planet. Once the existence of the local void became widely acknowledged, astronomers began studying its shape more carefully. Voids can be irregular, stretched, or distorted by the structures surrounding them. The local void appears to have a complex outline, expanding in some directions while connected to smaller underdense regions in others. As telescopes and surveys improved, more faint galaxies were detected around the void's edges, allowing scientists to trace the boundaries more accurately. These discoveries confirmed that the void occupies a substantial portion of the sky and stretches deep into space behind and around the local sheet. One of the reasons the local void remained unclear for so long is the presence of the Milky Way itself. Our galaxy blocks a portion of the sky with its disk of stars and gas. This obscured region, known as the zone of avoidance, hides many galaxies behind its dense structure. For decades, the void looked even emptier than it actually was, simply because some of its boundary galaxies were hidden from view. As radio and infrared observations improved, scientists could peer through the dust, revealing galaxies that formed part of the void's perimeter. Even with these detections, the local void remained among the emptiest known regions in the nearby universe. Mapping the void involved more than just identifying where galaxies were sparse. It also required measuring the motion of galaxies near its boundary. The behavior of these galaxies gave additional clues about the void's influence. Galaxies closer to the densest regions showed the strongest motion toward those areas. Galaxies facing the void showed a consistent outward drift, and because galaxies on different sides of the void moved differently, the contrast helped define the void's shape and depth. This outward drift is one of the most important characteristics of voids as a whole. They don't remain still, they expand. The local void, like others, grows because galaxies around it gradually move away. The more they move, the emptier the region becomes. This expansion is not dramatic or rapid. It occurs across billions of years, but its effects are measurable. When researchers compared the positions and velocities of galaxies around the local void across different surveys, they found clear evidence that the void was becoming more underdense over time, just as expected from theoretical models. The local void is not completely empty. Some galaxies inhabit its interior, though they are fewer and often smaller than typical galaxies found in clusters or along filaments. These void galaxies tend to be isolated, without many neighbours. Their isolation affects their evolution. They undergo fewer mergers, less gravitational interaction, and fewer disturbances from nearby structures. This isolation allows astronomers to study how galaxies behave in calm environments compared to the crowded conditions of clusters. Studying these galaxies provides insight into how environment shapes star formation, gas dynamics, and the growth of galactic structures. One of the surprising findings about the local void is how its presence explains certain puzzles about the motion of nearby galaxies. For example, the Milky Way and Andromeda are approaching each other, expected to collide in a few billion years. Their orbits reflect the gravitational pull between them. But when astronomers examined the motion of the entire local group relative to more distant galaxies, something didn't add up. The motion suggested that the group was being pulled strongly in one direction, but there was also evidence of motion away from another direction. Only when the local void was included in the analysis did the full picture emerge. The group wasn't being pushed, it was moving because of the imbalance created by the void on one side and dense regions on the other. This realization helped clarify why the local sheet appears unusually thin. The void's expansion exerts a kind of shaping influence. As galaxies move away from the void, they tend to form a more coherent planar structure. The Milky Way and its neighbouring galaxies lie within this plane. The void's absence of mass allows the sheet to remain relatively undisturbed from one side, helping maintain its flatness. Meanwhile, the denser regions on the opposite side guide the sheet's overall drift. This combination of influences creates a unique environment that has shaped the local cosmic neighbourhood over billions of years. Another clue about the local void's significance came from comparing how different galaxies in the nearby universe accelerate. Galaxies closer to the dense regions accelerate more strongly toward them. Those closer to the void show slightly less acceleration, because the gravitational pull on that side is weaker. This difference, when measured across many galaxies, reveals the void's gravitational signature, not through active force, but through the lack of it. When enough galaxies near the void were mapped, the pattern became unmistakable. The galaxies were slipping away from the void as the denser structures pulled on them with greater strength. The more astronomers studied the local void, the more they realized it was not an isolated feature. It connects to other underdense regions beyond its immediate volume, forming part of a network of voids that weave between the bright filaments of the cosmic web. These connections help explain why the void is so deep in some directions. Instead of a single spherical empty region, the local void merges into neighbouring voids, extending its reach and influencing motion across larger distances. Even galaxies well beyond the local group respond to this extended underdensity, showing patterns of motion that reflect the shape of the void network. Understanding the local void also helped researchers better interpret the distribution of dark matter in our region. Dark matter forms the underlying gravitational skeleton of the universe. Galaxies gather where dark matter is denser, creating clusters and filaments. Voids form where dark matter density is lower. By studying the local void's boundaries, astronomers could infer how dark matter is arranged in its vicinity. They could estimate how much dark matter is missing from the region and how the surrounding structures compensate. This information helped refine models of how the local group moves through space. The local void's role becomes clearer when placed alongside the dense regions on the opposite side of the local sheet. These dense regions include clusters, superclusters, and filaments that together create a significant gravitational pull. When the void's low density is combined with the mass of these structures, the resulting difference explains much of the peculiar velocity of the local group. The void's presence reduces the gravitational pull from one direction, while the dense regions enhance the pull from the other. This combination produces the motion measured in the cosmic microwave background and confirmed through galaxy surveys. What makes the local void particularly interesting is how close it is to us. We live on the boundary of this enormous region of underdensity. This proximity means even small details about the void influence our understanding of the cosmic environment. If the void had been located farther away, its effect might still be noticeable, but not as clearly. The fact that we live near its edge provides a unique perspective. It allows astronomers to measure how a major void shapes the motions of galaxies that exist right beside it. This makes the local void one of the most studied underdense regions in the nearby universe. As observations continue, the map of the local void becomes more detailed. New galaxies are discovered along its boundaries, refining the shape. Better distance measurements improve estimates of how fast galaxies are moving away from it. Simulations of cosmic structure formation help predict how the void will evolve over billions of years. These tools gradually reveal the void's full role in shaping our part of the universe. And as the understanding grows, so does the clarity with which the local group's motion can be explained. The local void may seem like a quiet neighbour, and in many ways it is. It lacks the dramatic features that make clusters and superclusters visually striking. But its quietness is part of what makes it so influential. Its emptiness creates contrast. That contrast shapes the gravitational landscape, and that landscape guides the motion of galaxies like ours. The local void doesn't need to do anything actively. Simply by having less matter, it plays a key part in the network of forces that shape our journey through space. As astronomers explored the local void more deeply, a natural question emerged from the data. If this region was so underdense and seemingly empty, what exactly filled the space inside it? The first instinct might be to imagine it as a hollow region containing nothing at all. A vast stretch of transparent space with no galaxies, no dust, no dark matter, just an enormous bubble of pure emptiness. But the closer scientists looked, the more they realized that even the emptiest regions of the universe are not truly empty. The concept of empty space has a different meaning in cosmology than it does in everyday life. In the universe, emptiness is a matter of comparison, not an absolute condition. At the simplest level, a void contains far fewer galaxies than the cosmic average. But fewer does not mean none. Even inside the most underdense voids, a small number of galaxies remain. Tiny, isolated specks living in quiet solitude, evolving differently from their counterparts in crowded environments. These galaxies are often faint and difficult to detect. They produce less light, have fewer stars, and possess limited material to fuel the kind of star formation that would make them stand out. Their lonely existence contributes to the impression that a void is empty, yet they provide valuable clues about how galaxies develop in environments where interactions are rare. The idea that even seemingly empty regions contain structure becomes clearer when considering the distribution of dark matter. Dark matter is invisible, but it exerts gravitational influence across space. Its presence shapes the motion of galaxies and forms the underlying framework for the cosmic web. In voids, dark matter is present but at much lower density than in surrounding regions. It forms faint strands and delicate patterns that barely register compared to the thick filaments located elsewhere. These thin threads of dark matter can still host small galaxies, but their mass is too low to form the kind of rich structures found outside voids. Even in emptiness, the cosmic web persists, only in a softer and more subdued form. Understanding why empty space is not truly empty also requires looking at the behavior of intergalactic gas. Between galaxies, even in regions that appear empty, thin traces of hydrogen gas stretch across vast distances. This gas is extremely diffuse, far thinner than the best vacuum humans can create in a laboratory, but it is present and it plays a role in shaping the thermal history of the universe. Over billions of years, this gas cools, heats, flows, and occasionally participates in the formation of new stars under the right conditions. In voids, the gas density is lower, making these processes less common, but not entirely absent. Observations using sensitive instruments reveal the faint fingerprints of this gas through the way it absorbs certain wavelengths of light from distant sources. Even the quiet interior of the local void holds such traces. When astronomers speak about empty space in cosmological terms, they also refer to the expansion of the universe itself. Space is not a static backdrop, it is dynamic. It stretches over time. Even regions that contain little matter participate in this expansion, and because voids contain so little mass, they expand slightly faster than denser regions. This difference contributes to the growth of voids over billions of years. The expansion inside a void is not dramatic or rapid, but the reduced gravitational pull from within allows the surrounding matter to continue drifting outward. As a result, the void becomes more empty with time, even though it was never entirely empty to begin with. Another aspect that shows why empty space is not truly empty lies in the presence of background radiation. Everywhere in the universe, including inside voids, the cosmic microwave background fills space with a faint glow. This glow is uniform, smooth, and present in every direction. Even the emptiest voids contain this radiation. It passes through without obstruction because there are so few galaxies to absorb or distort it. The presence of this radiation makes voids ideal places for testing cosmological theories. The smoothness of the background signal helps scientists identify subtle effects, such as slight temperature shifts caused by the motion of galaxy clusters or the gravitational influence of large structures. One might imagine a void as a quiet room, free of distractions, where any small disturbance becomes noticeable. In the case of the universe, a void is a region where subtle patterns in the cosmic background become easier to detect. Researchers use these regions to study how matter bends and warps space, how temperature fluctuations reveal the movement of galaxies, and how the universe expanded in its early years. Even emptiness becomes a tool for measurement, highlighting the structure that surrounds it by providing a backdrop with fewer complications. Another important detail is that voids are not isolated pockets cut off from the rest of the universe. They connect to other voids, forming a network of underdense regions that weave between the brighter parts of the cosmic web. These connections allow small amounts of matter to drift through, following the faint gravitational pathways shaped by the underlying dark matter. This network makes the concept of emptiness more fluid. Instead of being thought of as standalone bubbles, voids become part of the larger pattern of the universe. Their emptiness makes sense only when compared to the brighter filaments and clusters around them. As astronomers refined measurements of the local void, they realized it isn't a single clean shape. It has extensions, pockets, and regions where the density dips at different levels. Some parts of it connect to neighbouring voids, while other parts remain enclosed by clearer boundaries. This complexity shows that even within emptiness, structure exists. The density may be low, but the shape of the void is sculpted by the overall distribution of matter. These subtle differences allow astronomers to study how voids merge, how their boundaries shift, and how they grow over cosmic time. Voids also help researchers understand the balance of forces governing the universe. They provide evidence that gravity pulls matter together, while the expansion of the universe spreads it apart. In dense regions, gravity dominates, keeping galaxies close and forming clusters. In voids, expansion becomes more noticeable because the pull of gravity is weaker. This combination of effects shapes the cosmic landscape. The local void is a clear example. Its low density means that galaxies around it feel stronger gravitational influence from other directions. Over time, this has guided the motion of the local group and shaped the thin structure of the local sheet. Understanding what lies inside the void helps explain why the region around it looks the way it does. One of the most compelling reasons to study empty space is that the properties of voids challenge models of cosmic evolution. The size, distribution, and behaviour of voids must match predictions from simulations of how the universe formed. If the voids were too large or too small compared to these predictions, it would suggest that something about the cosmological model was incorrect. For example, if dark matter behaved differently, the pattern of voids would change. If the universe expanded at a different rate, the growth of voids would be altered. By comparing real voids like the local void to simulated ones, scientists can test how well their theories match observation. In this way, emptiness becomes a powerful tool for verifying the underlying physics of the universe. Another interesting feature of voids is the behaviour of galaxies that inhabit them. These galaxies, few in number and often isolated, evolve slowly. Their star formation histories tend to be more subdued. They experience fewer interactions that would disrupt their shape or fuel new bursts of star formation. As a result, they often retain characteristics that offer insight into earlier stages of galaxy formation. Studying these galaxies allows astronomers to understand how environment influences growth. Comparing them to galaxies and dense clusters highlights how different surroundings lead to different evolutionary paths. This contrast helps refine models of galaxy formation and the role that interactions play. In the local void, the galaxies found within its interior tend to be small, irregular, and faint. They display fewer signs of recent mergers. Their shapes are often asymmetric because they have not been sculpted by gravitational encounters. Their gas content can vary widely, and their star formation rates often show periods of quiet activity, influenced mainly by internal processes rather than external triggers. These galaxies offer valuable clues about how galaxies behave when left mostly alone, shaped primarily by their own internal dynamics. Even though voids contain matter, the overall density remains significantly lower than the cosmic average. This low density influences the rate at which voids grow. Regions with lower density exert less gravitational pull, allowing expansion to dominate more strongly. The local void, for example, appears to have grown over billions of years as galaxies around it drift away. This growth is gradual, steady, and consistent with predictions from cosmological models. As the void expands, galaxies at its edges experience slight changes in motion. They continue to drift outward, contributing to the void's deepening emptiness. The behaviour of galaxies near the void provides another important piece of evidence that empty space isn't truly empty. When astronomers measured the velocities of galaxies around the local void, they noticed a consistent pattern. Galaxies moved away from the void at speeds that suggested the gravitational influence of nearby structures was stronger than any influence inside the void. This result aligns with the idea that emptiness is defined not just by what is absent, but by how that absence shapes motion. The void's presence becomes noticeable through the behaviour of the galaxies at its boundary. even though the void itself contains little that can be observed directly. As scientists gathered more data, they developed a clearer understanding of the local void's role in shaping the motion of the local group. They recognized that the void's low density wasn't enough on its own to explain the full motion, but when combined with the mass of the dense regions on the opposite side, the pattern of movement made sense. The void contributed part of the gravitational imbalance, and the dense regions contributed the rest. Together, these influences created the layered motion that astronomers refer to when discussing the great cosmic tug. This understanding shows how emptiness plays a role in the larger structure of the universe. It doesn't act alone, but it alters the balance in ways that shape the paths of galaxies. Another aspect of why empty space isn't truly empty comes from the concept of dark energy. Dark energy permeates all of space and influences the expansion of the universe. It is not affected by the distribution of matter. Its presence means that even regions with very little matter still experience the same underlying expansion force. Dark energy contributes to the behavior of voids by allowing space to expand at a consistent rate regardless of density. This is part of why voids grow. Their low matter density means gravity has less strength to counteract expansion. As a result, voids become more prominent features of the cosmic landscape over time. Understanding voids also provides insight into the shape of the cosmic web. The bright filaments and clusters that capture our attention form because matter drifted away from the underdense regions toward the denser ones. Without voids, the cosmic web would look very different. The balance between empty and filled space shapes the universe at every scale. The presence of voids allows the filaments to form more clearly. Their emptiness defines the structure around them. The local void as part of this network helps illustrate these ideas. It is a large, quiet region that influences the motion of galaxies around it. It grows slowly as galaxies drift away. It contains thin strands of dark matter, faint gas, a handful of isolated galaxies, and the ever-present cosmic microwave background. It is empty only in comparison to the denser regions nearby. Its emptiness has shape, structure, and physical consequences, and its presence helps guide the motion of our galaxy group. As astronomers deepen their understanding of the local void and the broader network of underdense regions that fill much of the universe, a curious idea began to surface. Galaxies around these voids seemed to behave as though they were being pushed away. They drifted outward, increasing the size of the voids over billions of years. The motion looked almost as if something inside the void was exerting pressure, urging the galaxies outward. But when researchers examined the data more closely, it became clear that nothing of the sort was occurring. Voids weren't pushing anything. They didn't need to. The galaxies moved because the gravitational pull from elsewhere was stronger. And this simple difference created the appearance of a push, even in the absence of any real force pushing outward. Understanding this behavior requires stepping into the way galaxies respond to gravity on large scales. When matter is unevenly distributed across the universe, galaxies move toward regions where the density is higher. They follow the gradients in the gravitational field, sliding along the invisible contours shaped by mass. In a region with more galaxies, more clusters, and more dark matter, the gravitational pull is stronger. In a region with fewer galaxies and less mass, the pull is weaker. This difference creates motion. The galaxies don't rush or accelerate dramatically. Their motion is steady, guided by gravitational landscapes that span tens or hundreds of millions of light years. Voids represent some of the lowest density regions in the universe. They contain fewer galaxies and less dark matter. Their gravitational pull is weaker. This weakness is crucial because it means that galaxies at the edges of voids feel a stronger pull toward the surrounding filaments and clusters than toward the void's interior. Over time, this pulls them outward, away from the void. The movement looks like a push, especially when traced through maps of galaxy motion, but it is simply the result of unequal gravitational forces. The side with more mass wins. This concept becomes easier to grasp when looking at the motion of galaxies near the boundary of the local void. Observations show that many of these galaxies drift outward at speeds higher than expected from the universe's expansion alone. This outward drift indicates that the void contributes to a gravitational imbalance. It's not exerting a force, it's creating a region where there is less force, and because the surrounding areas contain more matter, the galaxies slide away naturally. From the perspective of a single galaxy near the void's edge, the motion is subtle. That galaxy doesn't sense anything pushing it. It simply feels a slightly stronger pull from the side with the dense structures. Over millions of years, this shift in direction adds up. Over billions of years, it becomes measurable. This long-term motion helps explain why voids grow, why galaxies cluster where they do, and why the universe looks the way it does on the larger scales. The local void offers a clear example of how this process unfolds. As galaxies along its boundary move away, the void becomes even emptier. The surrounding filaments grow more pronounced. The local sheet, which includes the Milky Way and many neighbouring galaxies, is shaped in part by this outward drift. The sheet doesn't collapse into the void or fall inward. Instead, it slides gently away, following the gravitational influences of the denser regions on the opposite side. This behaviour can feel counterintuitive because the idea of being pushed is familiar. We experience forces through physical contact in everyday life, but gravity works differently. It's a pull-only interaction. It never pushes. When something appears to move away from an empty space, the instinct is to assume something must be pushing it. But in cosmology, motion always reflects the distribution of mass. Galaxies drift away from voids because mass is greater elsewhere. The data that reveal this behaviour came from a number of different sources. Surveys mapping the redshift of galaxies provided the first clues. Redshift data shows how fast galaxies are moving away due to expansion, but it can also reveal additional motions layered on top. When astronomers subtracted the effect of cosmic expansion, a residual drift remained. This drift pointed away from the local void. Subsequent distance measurements confirm that the galaxy's motion was too fast to be explained by expansion alone. The void's presence was creating a gravitational imbalance. This imbalance becomes easier to visualize when you picture the cosmic web as a kind of uneven landscape. The dense regions are hills, the voids are valleys. But this valley analogy can be misleading if taken too literally, because galaxies don't roll into voids the way balls roll into real valleys. Instead, they move toward the hills. Gravity pulls them uphill toward the denser structures, not downhill into the emptier ones. The cosmic terrain is inverted when compared to everyday experience. Dense regions are where gravity is strong, voids are where gravity is weak. Galaxies travel toward the strongest pull, leaving the weak regions behind. Over time, this movement sculpts the shape of voids. Small voids merge to become larger ones. The edges sharpen. The centre becomes even less populated. The local void is believed to have grown significantly over billions of years, not because something inside it expanded aggressively, but because everything around it continued drifting outward. This expansion is similar to the behaviour of soap bubbles merging into a larger bubble, but the physics is entirely different. The analogy helps illustrate the growth, but the cause stems from the uneven pull of mass, not from pressure differences. The idea that voids push without pushing becomes even clearer when we consider the behaviour of galaxies at different positions around the local void. Some galaxies are closer to the void, and they experience a weaker gravitational pull from the direction of the void. Others are farther away, closer to the dense regions. They feel stronger pull and move accordingly. By comparing these different motions, astronomers can map the shape of the void and estimate the distribution of mass around it. When they do this, they consistently find that the galaxies on the void-facing side move outward more strongly than galaxies on other sides. This consistent outward motion is one of the defining characteristics of void boundaries. Another key piece of evidence comes from studying how voids influence the motion of galaxy groups. The local group, which contains the Milky Way, Andromeda, and dozens of smaller galaxies, sits near the boundary of the local void. Its peculiar motion, a speed of around 600 km per second relative to the cosmic microwave background, cannot be explained solely by the gravitational pull of dense regions ahead. The void behind contributes by providing an area with much less mass. The local group moves because the combined pull of the dense regions and the absence of comparable pull from behind create a net force. This net force is the origin of the great cosmic tug that astronomers discovered when studying the peculiar motion of galaxies. Over time, scientists developed more sophisticated ways to measure how voids influence galaxy motion. One method involves looking at how the cosmic microwave background is distorted by the motion of galaxy clusters. The imprint of this motion in the background radiation provides information about the direction and speed of galaxy drift. Another method uses the distribution of galaxy distances, comparing those distances to what would be expected from uniform expansion. Deviations from the expected pattern reveal the influence of nearby voids and dense regions. When these data sets are combined, a clear picture emerges. Voids create outward flows not through force, but through gravitational contrast. This concept becomes especially important when studying how galaxy clusters move across the cosmic landscape. Clusters are massive structures with thousands of galaxies. Their motion is not influenced by small features, but by large-scale patterns in the density field. When clusters near voids move outward, it confirms that the voids play a role in shaping motion across vast distances. The local void, while relatively small compared to some of the largest voids in the universe, still influences motion across tens of millions of light-years. This influence extends beyond the local group. Galaxies in neighbouring groups and sheets show similar drift away from the void. The behaviour of galaxies within voids also provides insight into this phenomenon. These galaxies tend to have slower peculiar velocities because they are surrounded by low-density regions. They feel less gravitational pull from any direction. This reduced influence means they move primarily with the expansion of the universe. Their environment is calm, contrasted sharply with galaxies near the edges of voids, which are tugged more strongly by the dense regions outside. This difference in motion helps confirm the idea that voids create an outward drift through lack of pull rather than through any active force. Another important detail is that voids are not uniform. They contain subtle variations in density. Some areas inside a void might have slightly more dark matter, or a small group of faint galaxies. These variations influence motion in small ways, creating a more complex flow pattern. Astronomers use simulations to study these variations and compare them to real observations. The simulations show that the motion of galaxies around voids is consistent with the gravitational influence of the surrounding structures. When the mass distribution is modelled accurately, the outward drift emerges naturally. This agreement between theory and observation strengthens the conclusion that voids push without pushing. The expansion of voids also has implications for how the cosmic web evolves over time. As voids grow, they stretch the filaments between them. The filaments become more elongated and clusters become more pronounced. The voids deepen and the dense regions grow denser. This relationship is self-reinforcing. The more the voids expand, the more matter accumulates in the bright regions, and the larger the gravitational gradients become. These gradients guide the motion of galaxies across the cosmic web. The local void plays a role in shaping the filament that contains the local group, influencing the shape of the local sheet and the surrounding galaxies. As researchers investigated the local void further, they found that its influence helps explain several puzzling features of the local universe. For example, the Milky Way's motion relative to nearby galaxies, which once seemed inconsistent with predictions, becomes easier to understand when the void's influence is included. The local sheet's flattened shape matches what simulations predict when a large void lies on one side. The peculiar velocities of galaxies in the nearby universe become more coherent when the void is accounted for. These findings show that the local void is not a minor feature. It is a major part of the gravitational landscape in our region. This understanding shifts the way astronomers think about empty space. Instead of seeing it as passive or irrelevant, they recognize it as an active contributor to the universe's structure. The absence of matter has consequences. It alters the motion of galaxies. It shapes cosmic flows. It influences how clusters form and how filaments stretch. Emptiness is part of the architecture of the universe. Much like the beams and supports inside a building shape the overall structure, even if they don't draw attention at first glance. The realization that voids push without pushing is one of those insights that clarifies many seemingly disconnected observations. It connects the motion of the local group to the larger cosmic web. It explains how voids expand and why galaxies cluster where they do. It helps researchers understand why the local universe appears as it does, with its pattern of filaments, sheets, and underdense regions woven together into a coherent structure. The local void, quiet and unassuming, becomes one of the key players in this story simply through its lack of mass. As astronomers learned more about the way galaxies respond to the uneven distribution of matter across the universe, one particular region continued to draw their attention. It wasn't just a single cluster, nor a simple gathering of galaxies. It was something far more complex and substantial, large enough to influence the motion of thousands of galaxies, including our own. This region came to be known as the Great Attractor. The name was introduced long before its nature was understood, chosen because the motions of galaxies seemed to point toward a spot in the sky where something massive appeared to be pulling on them. And while the name carried a sense of mystery, the underlying reason for the interest was much more straightforward. The gravitational pull from that region was measurable in the peculiar velocities of galaxies across the local universe. The story of the Great Attractor begins with those same motions that led scientists to notice the local void's influence. When astronomers measured how galaxies moved relative to the cosmic microwave background, they found that many nearby galaxies, including those in the local group, were drifting toward a particular patch of sky. This drift was significant enough that it became impossible to ignore. It suggested that a dense region of space lay in the direction of the constellation Centaurus, beyond the zone of avoidance where much of the Milky Way's dust obscures the view. Early on, researchers had difficulty determining exactly what lay in that region. The Milky Way blocks a large portion of the sky, hiding distant galaxies behind its thick band of stars and gas. This makes the zone of avoidance one of the most challenging areas to map, but new instruments allowed astronomers to observe the region in wavelengths that passed more easily through the dust. Radio observations helped detect distant galaxies by picking up the signals from their hydrogen gas. Infrared observations revealed structures otherwise hidden in visible light. As these tools improved, a clearer picture began to form. Behind the obscuring dust lay a massive concentration of galaxies, including a large cluster known as the Norma cluster. This cluster, along with surrounding structures, appeared to be part of an extended complex of mass. Although not as large as some of the most enormous superclusters known, the region contained enough matter to produce a substantial gravitational influence. The more scientists mapped it, the more they realized why it had appeared so prominently in measurements of galaxy motion. It was indeed a major contributor to the peculiar velocities seen across the local universe. But the story did not end with identifying the Great Attractor. As the data accumulated, it became clear that this region could not be the only source of the motion. The velocities were too large to be explained solely by the mass of the clusters in the area. Additional mass needed to be accounted for. This realization led researchers to look beyond the Great Attractor deeper into space. Behind the region, farther still in the direction of the Centaurus constellation, lay another massive structure, the Shapley supercluster. The Shapley supercluster contains some of the densest concentrations of galaxies in our cosmic neighborhood. Its clusters are enormous, each consisting of thousands of galaxies bound together in intense gravitational environments. The supercluster extends across hundreds of millions of light years, forming one of the most significant density peaks in the nearby universe. When scientists considered the combined mass of the Great Attractor and the Shapley supercluster, they realized that this pairing could account for much more of the drifting motion. However, even with these massive structures included, the calculations still didn't perfectly match the observed velocities. Something seemed to be missing. It wasn't that the Great Attractor and the Shapley supercluster were insufficient. It was that the models assumed equal contributions from all directions. Yet galaxies were not only moving toward these dense areas, they were also moving away from something else. That something, as later analyses confirmed, was the local void. The local void became the shy opposite force in this story, not because it exerted a literal push, but because its absence of mass allowed the forces from the opposite direction to dominate. When scientists included the void in their calculations, the numbers aligned more naturally. The local group wasn't being pulled solely by the Great Attractor or by Shapley. It was moving because the dense regions ahead were tugging more strongly, while the void behind tugged far less. This imbalance created the full peculiar velocity seen in the data. This realization marked a turning point in understanding the complexity of the local universe. Instead of seeing the Great Attractor as the single explanation for the motion of galaxies, researchers began to see a layered effect. The Great Attractor provided part of the influence. Shapley added another layer. The local void contributed by weakening any gravitational influence from behind. Together, these factors formed a more complete picture of why galaxies in the nearby universe move the way they do. The term Great Attractor persists, but astronomers now know that it is not a single structure. It's part of a much larger gravitational environment that includes clusters, filaments, and superclusters, all contributing to the overall motion. The way galaxies drift toward this region reflects the distribution of dark matter as well. Much of the mass influencing their motion is invisible. Dark matter forms the backbone of the Great Attractor region, shaping how galaxies cluster and move. Although dark matter cannot be seen directly, its influence can be inferred from the behavior of galaxies and the gravitational lensing of background light. Understanding the Great Attractor becomes clearer when one considers the distances involved. It lies roughly 150 to 250 million light-years from Earth, depending on which part of the complex is being measured. The Shapley supercluster lies even farther, roughly 600 million light-years away. These distances highlight just how far gravitational influence can extend. Even at such vast separations, the mass in these regions shapes the motion of entire galaxy groups. Gravity weakens with distance, but on cosmic scales, the sheer amount of mass compensates for the distance. A supercluster with thousands of galaxies can influence the motion of galaxies hundreds of millions of light-years away. Meanwhile, the local void lies on the opposite side of the local group, its emptiness contributing to the gravitational imbalance. This opposite influence is subtle but important. It doesn't act as a push, it simply provides less pull. The result is a motion that seems directed toward the Great Attractor but is, in reality, the combined effect of all the mass around us and all the empty space nearby. This understanding explains why the Great Attractor seemed so mysterious at first. Scientists were working with incomplete data. They knew galaxies were moving toward a certain region, but didn't yet know what lay behind the dusty plain of the Milky Way. They didn't yet know that the local void played a meaningful role. They didn't know the true scale of the Shapley supercluster. It took decades of observations, new technology, and improved models to assemble the complete picture. What looked like a single hidden mass pulling everything in its direction turned out to be part of a larger network of structures, influencing motion from multiple directions. As researchers mapped the Great Attractor more precisely, they realized that its influence is only part of a much broader flow known as the Laniakea supercluster. Laniakea is the supercluster that contains the Milky Way. It spans over 500 million light-years and includes many galaxy groups and clusters connected through gravitational flows. The Great Attractor sits near the center of this supercluster, acting as a kind of gravitational basin where the flow of galaxies converges. The motion of the local group toward the great attractor is part of this larger flow. But even within Laniakea, the presence of the local void helps determine the direction and speed of the flow. This interplay between dense regions and voids shapes the cosmic web. Dense regions pull, voids contribute through their lack of pull. The balance between these forces guides the motion of galaxies from one region to another. The great attractor and the local void represent two ends of this balance in our immediate environment. One side contains clusters and superclusters filled with mass. The other side contains an enormous underdense region. The local group moves accordingly, following the uneven gravitational landscape that stretches across the local universe. As astronomers examined this behavior across larger distances, they found similar patterns elsewhere. Other galaxy groups near large voids showed the same outward drift. Other clusters near major mass concentrations showed similar inward motion. The great attractor was not unique. It was simply the closest example of a more general phenomenon. The universe is filled with these gravitational patterns, forming a complex network of motions shaped by the distribution of mass and emptiness. Understanding the great attractor and the shy opposite force of the void brings clarity to the layered motion previously seen in the local group. Each part of the motion reflects a different scale of gravitational influence. On the smallest scale, galaxies within the local group orbit their common centre of mass. On slightly larger scales, the local group drifts along the plane of the local sheet. Beyond that, the sheet moves away from the local void. And on even larger scales, the entire region drifts toward the great attractor and the Shapley supercluster. These layered motions combine into the peculiar velocity seen in the cosmic microwave background. This layered motion also helps explain why galaxies in the local group appear to move differently when measured relative to various reference frames. Depending on whether the motion is measured relative to the cosmic microwave background, the local sheet, or the surrounding galaxy groups, the numbers change. But when each layer of motion is considered separately, the patterns align. The local void, the great attractor, and the Shapley supercluster each influence one part of the motion. Combined, they create the full picture. The deeper scientists looked, the more they realized that the great attractor was not an anomaly. It was a signpost marking a dense region within the cosmic web. Its influence, combined with the absence of mass in the local void, shapes the path of galaxies in our region. The shy opposite force, the quiet emptiness behind us, becomes just as important as the dramatic mass concentrations ahead. Together, they define the gravitational landscape through which we travel. When astronomers first set out to map the local universe in detail, they didn't expect to stumble upon a puzzle that would linger for decades. They assumed that if they could measure enough galaxy positions, enough velocities, and enough distances, eventually the pattern of motion in our cosmic neighbourhood would settle cleanly into place. But as the surveys expanded and the data accumulated, something unexpected kept appearing in the numbers. On one hand, galaxies were drifting in the direction of dense regions that matched the predictions of gravitational models. On the other hand, the overall motion seemed stronger than the pull from those regions alone. It was as if a piece of the gravitational landscape was missing. Something significant had been overlooked. This discrepancy wasn't immediately obvious. Early measurements were limited by technology. Galaxy velocities carried uncertainties. Distance measurements were also difficult, relying on indirect methods that required careful calibration. But even with these limitations, researchers could see that the local group, the collection of galaxies that includes the Milky Way and Andromeda, was moving at a considerable speed relative to the cosmic microwave background. The direction of that motion could be identified, the magnitude could be calculated, and the causes could be estimated. But when they compared the motion to the gravitational pull of known structures, the numbers didn't fully align. Scientists expected that the great attractor, the mass concentration in the direction of the Centaurus constellation, would explain most of the motion. The early surveys pointed clearly toward it. But when researchers estimated the mass needed to produce the observed velocities, the answer came up short. Either the Great Attractor wasn't as massive as expected, which seemed unlikely based on what was visible, or something else was contributing from another direction. That something else wasn't easy to identify, because the gravitational pull from distant superclusters and filaments blends together into a combined effect. The structure of the universe is too complex to dissect in simple, one-direction-at-a-time models. This mismatch between observed motion and estimated pull motivated astronomers to take a closer look at the local density field. They turned to galaxy surveys that mapped not only where galaxies were located on the sky, but also how far away they lay. These three-dimensional maps allowed researchers to estimate the mass density around the local group. The regions in front of us, toward the Great Attractor and the Shapley supercluster, showed high density as expected. But the region behind us was strangely quiet. Instead of clusters or filaments, there appeared to be a large expanse with very few galaxies. This underpopulated region was eventually recognized as the local void. Still, that recognition didn't occur all at once. The earliest galaxy maps simply showed areas where telescopes had not been able to detect much. Some of these areas were obscured by the Milky Way's dust. Others lay at distances where early surveys lacked sensitivity. Researchers couldn't assume a region was empty just because it contained few detected galaxies. It might have been filled with faint structures hidden from view. So the apparent emptiness behind the local group wasn't initially treated as a genuine cosmic void. It was treated as a blind spot. But as the quality of surveys improved, the blind spot began to shrink. Radio observations revealed faint galaxies behind the dust in the zone of avoidance. Infrared surveys detected structures otherwise invisible in optical wavelengths. Distance measurements became more reliable through the use of standardized candles such as Cepheid variables and Type Ia supernovae. Gradually the map of the local universe filled in, and as the data improved, a striking pattern emerged. The suspected underdense region remained underdense. Even with the new detections, it was still nearly empty compared to the surrounding areas. This finding raised an important question. If a large region behind the local group contained so little matter, how had its influence been overlooked for so long? To answer that, one must consider the way astronomers originally interpreted galaxy motion. They had focused primarily on the pull from dense regions. Gravity pulls, so the areas with lots of mass were assumed to be the main drivers of peculiar velocities. That assumption wasn't wrong. It just wasn't complete. The lack of pull from underdense areas matters too. If one side of a galaxy group lacks mass, the gravitational pull from the opposite side becomes relatively stronger. In the early models, the existence of significant low-density regions wasn't explicitly considered. The focus was simply on locating major attractors. This approach made sense at the time. Dense regions such as clusters and superclusters produce dramatic effects. They shape the motion of galaxies. They distort space. They cause gravitational lensing. They dominate the cosmic web. Voids, meanwhile, are quieter. Their influence is subtle, rooted not in what they contain but in what they lack. For many years, this subtlety meant that the role of voids in shaping motion was underestimated. The missing piece in the models was precisely the absence of matter. Once astronomers began to calculate the gravitational influence of the local void, the picture changed. The void didn't pull on the local group. It simply didn't pull back. This lack of opposing gravitational force meant that the pull from the Great Attractor and other dense structures was more effective. The peculiar velocity of the local group wasn't entirely the result of the mass in front. It was partly due to the lack of mass behind. This realization helped explain the larger-than-expected motion. Understanding how scientists noticed something was missing requires stepping through the challenges they faced in mapping the local universe. The zone of avoidance blocked large portions of the sky. Many galaxies lay behind thick dust clouds. Some populated regions were detected only in radio wavelengths. The patchiness of early maps made it difficult to distinguish between areas genuinely lacking galaxies and areas simply unobserved. The first large-scale redshift surveys didn't include faint galaxies. Distance measurements for many galaxies were uncertain. All of these limitations created gaps in the data that allowed the void to remain unnoticed. As these gaps were filled, scientists began to realize that the structure of the local universe was more uneven than expected. The asymmetric distribution of galaxies had implications for gravitational balance. If the universe were uniform, the motion of the local group would be simple to explain. But the universe is not uniform. Clusters, filaments, and voids create an intricate landscape that shapes motion at every scale. The peculiar velocity of the local group is the result of this complexity, and to fully understand that complexity, astronomers needed to identify the underdense regions as well as the overdense ones. The discovery of the local void as a major contributor came from combining several lines of evidence. The first was the sheer emptiness of the region in three-dimensional galaxy maps. The second was the clearer picture of the gravitational influence from the Great Attractor and Shapley. The third was the peculiar velocity of galaxies near the void's boundary. These galaxies were drifting away from the void faster than expected, consistent with models of void expansion. When all these pieces were placed together, the conclusion was unavoidable. Something important had been missing from earlier models. That missing component was the gravitational effect of the void. This realization marked a shift in cosmology. Voids were no longer viewed as passive regions with little relevance. They became recognized as key players in the large-scale structure of the universe. The local void in particular gained importance because of its proximity to the local group. Its influence helped explain several puzzles. The motion of the local sheet, the alignment of the peculiar velocity with certain structures, and the layered motion seen in the local universe all made more sense when the void's role was considered. One of the challenges in demonstrating the void's influence was showing that its effect was not limited to a single region. Astronomers studied the behavior of galaxies in other parts of the universe. They found that galaxies near the edges of voids consistently moved outward. This outward drift confirmed that voids contribute to motion across the cosmic web. It also helped validate the models used to study the local void. The patterns were consistent. In multiple regions, galaxies behave similarly near void boundaries. This consistency strengthened the conclusion that something had been missing from earlier calculations of gravitational influence. In addition to studying galaxy motion, researchers also modelled the distribution of dark matter in the local universe. Dark matter forms the scaffolding on which galaxies gather. In regions where dark matter density is low, visible structures are sparse. By comparing dark matter models to galaxy maps, astronomers could infer the presence of the local void, even in areas where galaxies were too faint to detect. These models confirm that the void extended deeply into the local universe, occupying a substantial region and contributing to the imbalance shaping the local group's motion. Another aspect of the investigation involved studying how voids evolve over time. Voids grow as galaxies drift outward. This growth means that the local void may have been less prominent in the past. Its influence would have increased slowly as it expanded. This gradual change helps explain why the void wasn't recognized earlier. The early universe contained smaller voids and less extreme differences in density. Only over billions of years did the local void become as large and empty as it is today. This means that earlier models of local motion might not have fully reflected the present structure of the universe simply because they lacked the resolution to capture the void's size and shape. As the concept of the local void became more established, scientists revisited earlier calculations with updated models. When they included the void's low density, the motion of the local group aligned more closely with the gravitational influences from the Great Attractor and Shapley. The previously unexplained component of the motion became clearer. The local void alone didn't explain everything, but it contributed significantly to the imbalance. Without accounting for it, the models consistently underestimated the observed drift. This improved understanding helped form a more complete picture of how the local group navigates the cosmic landscape. The local void sits behind us. the great attractor and Shapley sit in front. The gravitational forces from the front dominate because there is less opposing pull behind. This creates the peculiar velocity seen in the cosmic microwave background. The layered motion of the local sheet and the local group reflects the combined influence of all these structures. The idea that something had been missing in earlier interpretations became widely accepted as more detailed surveys were completed. The gap in the gravitational landscape behind the local group was no longer overlooked. Its presence became essential to understanding the direction and speed of motion, and with that recognition came the realization that voids, despite containing little matter, play an important role in shaping the paths of galaxies across the universe. This shift in understanding led scientists to pay closer attention to voids across the cosmic web. They began studying their shapes, their growth, their interactions with surrounding filaments, and their influence on galaxy evolution. The local void was no longer an anomaly. It was simply a nearby example of a common cosmic feature. What made it special was its proximity to the Milky Way and its significant role in determining the motion of our galaxy group. As astronomers gathered enough information to understand that the local void existed beside our galactic neighbourhood, the next question shifted toward how such a region changes over time. The idea of a void expanding might seem strange at first. If something is empty or nearly empty, it's easy to assume it would simply remain as it is, a quiet region that doesn't evolve in any meaningful way. Yet emptiness in cosmology behaves differently from how the word might suggest in everyday language. A void isn't a fixed cavity carved into space. It's a region shaped by motion, gravitational imbalance, and the slow shift of galaxies moving along the lines of the cosmic web. If galaxies drift outward, the boundary of the void grows, and if the void grows, its edges expand steadily, altering the structure of the nearby universe. To understand what it means for a void to expand, one must consider how the distribution of matter changes across cosmic time. Galaxies move not only because the universe is expanding, but also because gravity guides them toward regions of higher density. Over billions of years, these gentle drifts accumulate. The paths they follow reveal a great deal about the gravitational landscape around them. In the case of the local void, the galaxies along its boundaries show motions that indicate the void has been growing steadily. They move outward, away from the central region of low density, and their motion contributes to the gradual expansion of the void's volume. This outward motion has been measured using precise distance surveys. When astronomers began comparing distances to velocities for many galaxies spread across the edges of the local void, they noticed that the velocities were higher than expected from the expansion of the universe alone. The galaxies were not only receding due to cosmic expansion, they were also drifting outward more quickly than similar galaxies in regions without such pronounced voids. These measurements provided some of the first convincing evidence that the void was expanding. The galaxies behaved as though something was pulling them away from the centre of the void, even though the reality was very different. They weren't being pulled from within, they were being pulled from outside toward the surrounding filaments where mass was more concentrated. The edges of the void reveal this dynamic relationship. They mark the places where underdensity transitions into regions where galaxies are more common. This boundary isn't sharp. Instead, it blends across millions of light years. Mapping this gradient helps astronomers understand how voids evolve. The boundary moves outward as galaxies drift away, and the void deepens as matter continues to leave. This process occurs slowly, but it is continuous across cosmic time. Small voids merge with neighbouring voids. Larger voids grow wider. The cosmic web becomes more defined as structures tighten and empty regions expand. The local void is large enough that its expanding edges influence the shape of the local sheet. The local sheet contains the Milky Way, Andromeda, and several dozen other galaxies arranged in a relatively flat plane. The motion of this sheet reflects the pull from dense regions ahead and the lack of pull from behind. As the void expands, the sheet moves more coherently. The galaxies remain aligned along the thin plane, shaped partly by the absence of significant mass on one side. This configuration helps astronomers trace the boundaries of the void more clearly. The sheet's behaviour acts like a marker showing where the gravitational influences change. As the edges expand, the void doesn't become completely empty. There are still small galaxies within it, but they are few in number. Their isolation grows over time as the boundary galaxies move outward. The internal galaxies of a void offer unique insights into how a sparse environment affects their development. They experience little external disturbance, rarely interacting with neighbours or falling into clusters. Their star formation histories differ from those in crowded environments. They evolve slowly, influenced largely by internal processes rather than encounters. These galaxies allow astronomers to study how isolation shapes their behaviour. Even though the void expands, these internal galaxies reveal the faint traces of structure that persist inside. Understanding how the edges expand also requires looking at the behaviour of dark matter. While voids contain less dark matter than surrounding regions, they are not entirely devoid of it. The dark matter inside a void redistributes as galaxies move. It forms faint, underdense structures that provide a basic framework. As galaxies drift outward, the dark matter diffuses, creating an even lower density in the central region. Meanwhile, dark matter at the edges becomes slightly more concentrated as it collects near the rising density of surrounding filaments. This redistribution contributes to the shape of the void over time. The gravitational influence remains weak inside and stronger near the edges, reinforcing the outward drift. The measurements that revealed the expanding edges came from data gathered over many decades. Early surveys laid the foundation, but they lack the resolution needed to detect subtle motions. As instruments improved, astronomers could measure distances to galaxies with higher precision. They used techniques such as the Tully-Fisher relation, which connects the luminosity of a spiral galaxy to its rotation speed. They use surface brightness fluctuations for galaxies with older stars. They use Cepheid variables and Type Ia supernovae as standard candles. Each of these methods helped refine the distance estimates, and with more accurate distances the outward drift became clearer. The data revealed not only the speed of the drift but also its direction. Galaxies near the void's boundary were moving outward in a pattern consistent with void expansion. The pattern wasn't random. It followed the expected behaviour from simulations. In these simulations, voids expand because matter flows toward denser areas. The local void behaved exactly as predicted. This agreement between theory and observation strengthened the case that the void's edges were expanding steadily. One important realization was that void expansion is not something driven by internal pressure or any exotic force. It is a natural consequence of gravitational dynamics in an uneven universe. The void grows because there are no large structures inside to counter the pull from outside. The gravitational landscape guides galaxies toward areas rich in mass. Voids grow not because something drives them outward, but because everything else is drawn away from them. This slow reshaping of space adds an important piece to the understanding of cosmic evolution. It shows that emptiness is not a passive feature, but an integral component of how the universe organizes itself. Another interesting detail is that the expanding edges influence the way the cosmic web connects across large scales. The cosmic web consists of filaments, clusters, and sheets that form a complex network. The filaments connect dense regions like bridges between islands. The voids form the open spaces between these structures. As voids expand, they push the filaments slightly closer together. This doesn't mean the filaments collapse. It means that the shape of the network becomes more pronounced. The bright structures grow denser and more connected. The empty regions grow emptier. This interplay creates the striking contrast seen in large-scale maps of the universe. The local void's expanding edges play a role in this global process. By influencing the shape of the nearby filaments, the void helps define the local cosmic web. The sheet containing the Milky Way, for example, lies in a position shaped partly by the void's growth. The filament that extends from the local group into adjacent galaxy groups reflects the same influence. Even the alignment of certain structures in the nearby universe becomes easier to understand when the void's expansion is considered. Studying the expanding edges also provides insight into how matter flows across space. In dense regions, matter tends to fall inward, feeding the growth of clusters. In voids, matter flows outward, adding to the boundaries. This outward flow helps determine the size and shape of voids. The more matter that flows outward, the larger the void becomes. The rate of expansion depends on the amount of mass nearby. In areas of the universe where mass is distributed sparsely, voids can grow more quickly. In crowded regions, void expansion slows. The local void grows at a rate consistent with the surrounding mass distribution. Its expansion is not uniform in all directions. It grows more easily where neighbouring voids lie. It grows less where filaments block its spread. This directional growth leads to an irregular shape. The local void is not a perfect sphere. It has extensions and bulges. Some parts connect to other voids. Some are more enclosed. These irregularities help scientists identify the most significant pathways for mass flow. They also show how the edges respond differently, depending on local conditions. By studying these boundaries, researchers gain a deeper understanding of how the cosmic web behaves. Another component of the expanding edges involves examining the velocities of galaxies in different regions. Galaxies closer to the densest filaments experience strong gravitational pull. Their velocities carry the signature of these influences. Galaxies facing the void, however, show weaker acceleration. This difference creates the outward drift observed at the edges. Over time, the pattern becomes more pronounced. The void grows deeper as matter continues to leave. This deepening makes the influence of the void easier to detect. It shapes the nearby space in a way that gradually becomes measurable. The understanding of how voids expand also helps explain why the universe looks more structured today than it did billions of years ago. In the early universe, matter was distributed more uniformly. The density differences were present, but they were very small. Over time, gravity amplified these differences. Dense areas grew denser. Empty areas grew emptier. This amplification created the cosmic web. The voids became more pronounced. The filaments sharpened. The universe developed structure on every scale. The expanding edges of voids are part of this long-term evolution. The local void is large enough that its expanding edges affect the motions of thousands of galaxies. When astronomers map the peculiar velocities across the region, they can see the signature of the void's influence. Galaxies near the boundary move outward more quickly. The local sheet moves away from the void. The local group follows this motion. The combined effect becomes part of the layered motion detected when comparing velocities relative to the cosmic microwave background. The void's expansion contributes its share to the overall flow. As understanding deepened, the expanding edges became one of the clearest indicators of how the local void interacts with the surrounding universe. The void isn't a static feature. It continues to grow as matter flows out. This growth will persist for billions of years. Even though the expansion is slow, its influence accumulates over long time scales. The nearby structures respond to it gradually. The local group moves accordingly, guided by the gravitational landscape shaped partly by the void. Astronomers use these insights to refine simulations that model the formation of the cosmic web. The models show how voids evolve, how filaments shift, and how clusters grow. When compared to real observations, the models confirm that the local void behaves as expected. Its edges expand. Its shape reflects the mass distribution. Its influence on the motion of galaxies matches theoretical predictions. This agreement provides confidence in the broader cosmological framework and reassures scientists that they are interpreting the local universe correctly. As astronomers developed clearer maps of the large-scale universe, they began noticing patterns that repeated themselves in region after region. Voids did not simply exist as static pockets of underdensity. They grew. Their boundaries crept outward as galaxies drifted away from them. This movement wasn't dramatic on human timescales, but over hundreds of millions of years it produced measurable changes that reshaped the surrounding cosmic structure. The more scientists studied the details, the more evident it became that the relationship between voids and galaxies formed a fundamental part of the universe's evolution. Understanding why voids grow begins with recognizing how galaxies respond to gravity across great distances. Dense regions act like gathering points. They contain clusters, filaments, and superclusters where mass accumulates. These areas exert strong gravitational pull, drawing galaxies toward them. Voids, by contrast, contain very little mass. Their gravitational pull is weaker. This simple imbalance guides the gradual outward drift of galaxies that sit along the edges of voids. Over time, the combined effect of many galaxies drifting outward builds the structure that defines the void's expanding boundary. The local void provides a particularly clear example because it sits directly beside the region containing the Milky Way. Its influence is easier to measure due to proximity. When researchers compared the velocities of galaxies near the void's edge, they found consistent signs of outward drift. These galaxies weren't simply receding because of cosmic expansion. They were moving faster than expected. The extra velocity pointed to a gravitational imbalance. The galaxies were following the pull from denser regions while simultaneously moving away from an area with very little mass. This outward movement created a slow widening of the void. The growth of voids is not uniform. Some parts expand more quickly because they face neighbouring voids rather than dense filaments. Matter flows more easily into underdense areas when the surrounding landscape contains multiple regions of similar low density. This allows voids to merge and create larger structures. On the opposite side, where dense filaments block the void's expansion, growth slows. The local void displays this uneven behaviour. Certain extensions of it reach into other underdense pockets. Other parts run up against nearby filaments. The result is an irregular shape that reflects the distribution of matter in the surrounding environment. Galaxies at the edges reveal the details of these processes. Their motion gives clues about how quickly the void grows. By measuring the distance to dozens of galaxies around the local void and comparing those distances to their velocities, astronomers determine the magnitude of their outward drift. The data show that the void expands because matter continually slides away from its interior. That drift is not caused by the void itself acting as a force, but by the absence of matter within it. Gravity pulls more strongly from the opposite directions, guiding galaxies into denser regions where they become part of filaments or clusters. Voids also influence how galaxies evolve. Galaxies near the boundaries of voids tend to retain more gas than galaxies in denser regions. That difference arises because galaxies experience fewer interactions at the edges of voids. In crowded environments, galaxies often collide or pass close enough to disturb each other's gas reservoirs. These interactions strip gas, alter star formation rates, and reshape galactic structure. But near voids, galaxies face fewer encounters. Their gas remains more intact. Their star formation histories become quieter and more stable. Their shapes stay less disturbed. Studying these galaxies helps astronomers understand how environment affects galaxy evolution. The galaxies that live deep inside voids provide an even sharper contrast. Though rare, they offer a window into an environment where gravitational interactions with neighbours are minimal. Their isolation leads to fewer mergers. Their growth depends largely on internal processes. These galaxies present subtle differences in structure, luminosity and rotation that tell a different kind of evolutionary story. They often appear smaller, with lower star formation rates. Their gas content varies widely, shaped not by external triggers, but by long, gradual internal cycles. They serve as examples of how galaxies behave when left mostly undisturbed. As voids grow, they change the shape of the cosmic web. The empty regions widen. The filaments stretch between them, becoming more pronounced. The clusters sitting at intersections become denser. The contrast between filled and empty regions increases over time. This contrast makes the universe more structured. What began as small fluctuations in density after the Big Bang, tiny differences of 1 part in 100,000, have been amplified over billions of years. Voids deepened, filaments thickened, the overall pattern grew sharper. The local void contributes to this process, helping define the shape of nearby structures as it expands. Examining how galaxies flee from voids also provides insight into the overall flow of matter in the local universe. The motion of the local sheet, for instance, reflects the pull from dense regions and the lack of pull from the local void. The sheet moves as a coherent structure, shaped partly by this imbalance. When astronomers measure the velocities of galaxies across the sheet, they find that the galaxies move together, drifting in the direction of the Great Attractor and the Shapley supercluster, while moving away from the void. This layered motion confirms the role played by the void in shaping the local flow. The expansion of voids also appears in detailed simulations of the cosmic web. Using models based on dark matter and cosmic expansion, scientists recreate the universe's evolution from early times to the present. These simulations show voids merging, growing and stretching as matter flows away from them. The patterns match what astronomers observe. The local void behaves as expected for a void of its size and position. It grows where the surrounding mass distribution allows it. It contributes to the peculiar velocities of nearby galaxies. It helps sculpt the local structure. These simulations also reveal that voids expand faster than the average expansion rate of the universe. This happens because the gravitational pull inside a void is weaker. There is less mass to counteract the expansion. As a result, the void's interior expands more readily. This accelerated expansion contributes to the outward drift of galaxies near the edges. It is not a force produced by the void. It is simply the expansion of space happening more freely inside a region with little mass. The surrounding denser regions resist expansion more strongly due to gravitational attraction. This contrast leads to faster growth of voids relative to the cosmic average. Another outcome of void expansion is the subtle effect it has on the distribution of dark matter. Although dark matter does not interact with itself or with normal matter in the same ways that gas and stars do, it still responds to gravity. In voids, the dark matter density is low. As matter flows outward, the distribution becomes more diffuse. The dark matter gradually spreads outward along with the visible galaxies. The edges become slightly more defined as dark matter accumulates near the surrounding filaments. This redistribution helps shape the void structure. It also supports the idea that voids act as regions where matter naturally evacuates over time. Galaxies flee from voids because they follow the gravitational paths laid out by the surrounding mass. These paths are not straight lines. They curve through the cosmic web guided by the underlying dark matter distribution. Galaxies drift along these paths slowly. Their motion builds up over hundreds of millions of years. When astronomers track them using redshift data, they see the cumulative results. The outward motion reflects not only where galaxies are headed, but also where mass is missing. The lack of opposing pull from the void emphasizes the pull from the opposite side. The idea that voids influence the motion of galaxies even across great distances becomes clearer when considering the scale of the local void. It spans tens of millions of light years. Its edges cover an even wider region, when smaller neighbouring voids are included. The gravitational imbalance caused by such a large underdensity extends far beyond its boundaries. The local group positioned near one edge feels this imbalance as part of its motion. So do other nearby groups and sheets. Their velocities carry the imprint of the void's presence. As astronomers compared the motions of galaxies in different parts of the local universe, they found that void-induced flows were common. Other voids showed similar outward drifts. The galaxies near their edges moved in predictable patterns. The consistency across multiple regions supported the idea that voids played a significant role in shaping motion throughout the cosmic web. This realization helped reinforce the importance of accounting for voids in cosmological models. Without including them, predictions about galaxy motion would remain incomplete. One of the more subtle ways voids shape the cosmic landscape is through the way they influence the alignment of structures. Voids can cause sheets and filaments to tilt or stretch, depending on the direction of surrounding mass flows. In the case of the local sheet, the influence from the local void contributes to its relatively thin and coherent structure. The absence of mass on one side allows the sheet to maintain its flatness. The galaxies remain aligned in a broad plane because there is little gravitational pull from below to disrupt the arrangement. This configuration supports the idea that void growth has long-term effects on the shape of nearby structures. The continued expansion of voids also affects how galaxies interact with each other across large scales. As galaxies drift into denser regions, they encounter more interactions. These interactions can lead to mergers, gas stripping, and star formation changes. Meanwhile, the galaxies that remain in voids retain their quiet environments. This contrast contributes to the diversity observed in galaxy properties across the universe. Some galaxies become part of complex clusters with hundreds of interactions shaping their evolution. Others, near voids, evolve in relative solitude. Galaxies fleeing voids contribute to the overall flow that structures the universe. This flow helps form the boundaries between different regions of the cosmic web. It defines the edges of filaments. It shapes the outlines of clusters. It creates a dynamic environment where matter continuously redistributes across space. The local void's influence on this flow becomes one part of a much larger picture. As galaxies leave it behind, the void becomes more distinct. The surrounding structures become clearer. The landscape becomes easier to interpret. As the void continues to grow, astronomers can use its expansion to refine measurements of cosmic evolution. The rate of expansion reflects the influence of dark matter, dark energy, and gravity. By studying voids like the local void, researchers gain insight into how the universe behaves on large scales. These insights help improve models and refine predictions about the future shape of the cosmic web. As astronomers pieced together the motion of our galaxy group, the picture that emerged showed a region shaped by forces coming from multiple directions. This motion wasn't chaotic or unpredictable. It followed clear patterns once all the elements were considered. On one side of our position lay dense clusters and filaments, regions where mass had gathered over billions of years. These structures exerted a steady gravitational pull that guided galaxies toward them. On the other side lay a wide underdense region lacking much of that mass. This quiet area, our neighbouring void, offered little gravitational influence. Together, these opposing sides created a situation where our galaxy group moved along the path of greatest gravitational imbalance. The result of this imbalance placed us in a space shaped not by a single factor, but by the combined influence of many. The Milky Way sits inside a structure called the local sheet, a flattened arrangement of galaxies that includes Andromeda, the Triangulum galaxy, and several dozen smaller systems. This sheet moves as a coherent plane. Its motion isn't random, it reflects the forces acting on all its members. Understanding this motion required separating it into components. Each component points toward a different gravitational influence. Some components reflect the pull from nearby groups, others reflect larger scale attractions, and one component reflects the lack of pull from the vast region behind the sheet. Interpreting these layers makes it easier to understand the position we occupy in the cosmic landscape. One part of our motion traces back to the mutual gravitational pull between the Milky Way and Andromeda. These two galaxies are on a slow collision course, drawn together by their combined mass. Their motion toward each other occurs over billions of years. This local motion tells only a small part of the story. Beyond that lies the movement of the entire local group through space. This motion is aligned with the direction of the Great Attractor and the Shapley concentration farther beyond. These dense regions create a strong pull that shapes the general flow of many galaxies in the surrounding hundreds of millions of light years. But even these massive structures cannot fully explain the direction and speed of the local group's motion when considered alone. The velocity measured relative to the cosmic microwave background shows a magnitude larger than what the mass in front appears capable of producing. This mismatch puzzled astronomers for decades. When they added the influence of the local void, the imbalance made sense. The lack of mass behind the local sheet allows the gravitational influence from the front to exert more effect. With less pull coming from the side of the void, the combined effect of the masses ahead becomes more pronounced. The reason for our motion becomes clearer when viewed in this context. This dual influence means that our place in the universe is shaped by the presence of both dense and empty regions. The local void doesn't push the local group, it simply does not restrain it. Without matter behind us, the flow toward the denser regions becomes stronger. The local sheet, positioned at the interface between these two contrasting sides, reflects this arrangement. It drifts away from the void while moving toward the great attractor's larger gravitational basin. This dual motion creates a pathway through space that reveals the structure of our surroundings. When astronomers map the motion of galaxies in the nearby universe, they see several layers combining into the observed velocity. On one scale, individual galaxies follow the pull of their nearest neighbours. On a slightly larger scale, groups and sheets follow the pull of larger structures. On an even larger scale, these larger structures are drawn towards superclusters and vast concentrations of mass. Our motion reflects these multiple scales. The direction we move tells astronomers that we sit between a dense region that draws us in and a thin region that allows unbalanced pull from the other side. The local sheet's position is particularly important in understanding this balance. The sheet lies in a relatively stable plane shaped by the gravitational environment. Its thinness suggests that it formed where gravitational forces cancelled in certain directions, while remaining strong in others. The absence of significant mass below the sheet allowed it to remain flat. The presence of dense structures above drew its galaxies toward them. This arrangement created a kind of gravitational layering. The sheet developed because matter flowed away from the local void and toward the denser concentrations beyond. This motion becomes visible in the way galaxies within the local sheet share similar velocities. The galaxies move coherently, following the same broad direction. This coherence provides strong evidence that the void behind them plays a substantial role. The galaxies aren't responding to internal forces inside the sheet, they are responding to the larger environment. When researchers compare the velocities of galaxies across the sheet, they see them moving faster in the direction of the dense regions than galaxies farther from the void. This difference demonstrates the contribution of the low-density side to the overall flow. Studying these flows also reveals that our path through the universe is not determined by a single attractor. The great attractor contributes, the Shapley region contributes, the local void contributes. Each factor shapes part of the motion. The combination leads to the peculiar velocity we observe. Without considering the full distribution of matter and emptiness, the picture would remain incomplete. The layered approach provides the clarity needed to understand our place between the contrasting influences. Another aspect of this position involves looking at the shape of the large-scale structures surrounding us. The cosmic web outlines the arrangement of galaxies across the universe. It consists of filaments, sheets, clusters, and voids. The local sheet is one of these structures. It sits on the boundary of the local void. On its opposite side are filaments connecting to groups and clusters that lead toward larger concentrations. This arrangement gives astronomers context for understanding how galaxies arrived at their current positions. Our sheet formed where these influences met. Its motion continues to reflect these influences. Researchers have found that the local sheet moves as part of a broader flow that extends across the nearby universe. This flow guides galaxies along paths shaped by the underlying dark matter. The flow shows that our group of galaxies is part of a larger movement toward the densest regions in our surrounding volume. The flow does not lead directly into any single cluster. Instead, it moves first toward the great attractor region, then continues toward Shapley. This layered direction reflects the combined gravitational landscape. The presence of the local void helps create the backward component of the motion, ensuring that the forward component dominates. Galaxies outside the local sheet show different degrees of influence depending on their position relative to dense regions and voids. Some galaxies closer to the void display greater outward drift. Others positioned near filaments show stronger inward pull. These differences help reveal how motion depends on location in the cosmic web. Our place between pull and push becomes one instance of a more general phenomenon. Every region of the universe experiences a local balance between dense and empty areas. The specific configuration around the Milky Way gives rise to the particular motion we observe. These motions are measurable because the cosmic microwave background provides a reference frame. The background radiation fills the universe with an almost uniform glow. Any deviation from perfect uniformity in the radiation as observed from Earth indicates motion relative to that background. When astronomers measured this deviation, they found the signature of the local group's motion. The temperature differences in the background corresponded to a velocity of roughly 600 kilometers per second. This measurement provided a starting point for exploring the causes. The motion demanded explanation, and the explanation required examining both dense and empty regions. The existence of the local void behind the local sheet offered the missing factor. When scientists incorporated it into their models, the motion aligned with predictions. The gravitational influence from the front and the lack of influence from behind combined to produce the observed speed and direction. This understanding positioned our galaxy group between a region that draws it forward and a region that allows that draw to remain unopposed. The local void's presence didn't dominate the motion, it supplemented it. The great attractor and Shapley provided most of the pull. The void ensured that nothing slowed the drift. This balanced position affects not only the motion of the local group, but also the distribution of galaxies around it. The local sheet extends outward, with a shape influenced by the void. The galaxies remain aligned because gravitational forces on one side are weaker. Their velocities remain similar because they share the same large-scale influences. This configuration shows how cosmic structures take shape not only from the presence of mass, but also from its absence. The empty regions define the boundaries, they guide the flow, they allow the dense regions to exert more effective pull. When considering our place in the cosmos, it becomes clear that we occupy a transition zone. It is a region shaped by the contrast between mass-rich and mass-poor areas. The motion of our galaxy group is part of a larger pattern that spans hundreds of millions of light years. This pattern shows how the distribution of matter determines motion across vast distances. It also shows that emptiness cannot be ignored. Empty regions contribute to the landscape just as much as filled ones. The local void helps determine the direction we move. Without it, the motion would be weaker or differently oriented. Astronomers continue refining their understanding of this balance by collecting more data on galaxy distances and velocities. The more precise the measurements become, the clearer the picture gets. Even subtle features of the flow emerge. These features help confirm that our place between pull and push reflects the true balance of forces in the local universe. The local sheet's behavior matches what models predict for a sheet on the boundary of a major void. The outward drift from the void and the inward pull from dense regions work together to shape the motion. As researchers explore the local universe in greater detail, they uncover additional layers that contribute to the gravitational landscape. More distant structures play roles. Smaller voids connect to the larger one. Filaments branch into multiple directions. This complexity enriches the understanding of the cosmic web. But despite the complexity, the broader pattern remains clear. Our galaxy group sits between opposing influences. The void reduces gravitational pull on one side. The dense regions amplify pull on the other. This balanced position offers insight into the long-term evolution of our surroundings. As the void expands, the imbalance may become slightly more pronounced. As dense regions grow through continued accretion, their pull may also become stronger. The local group will continue drifting along the same general path, shaped by the combined influences. The motion will persist over billions of years. It will remain guided by the distribution of matter and emptiness. Understanding this position also helps place our galaxy in context. The Milky Way is not isolated. It moves as part of a larger structure. Its motion is not random. It reflects the gravitational environment of the local universe. The path we travel connects us to regions with far more mass and separates us from regions with far less. The local void, sitting behind us, ensures that the pull from in front remains significant. The great attractor and Shapley provide that pull. These factors combine to guide the local sheet's direction and speed. When astronomers examine the large-scale structure of the universe, one of the first things they notice is how unevenly matter is spread. Some regions contain dense, interconnected networks of galaxies forming clusters, filaments, and sheets. Other regions appear almost empty, with only a few faint galaxies scattered across enormous volumes of space. These contrasting environments create the cosmic web. The visible structures represent only a fraction of the universe's total volume. The rest is dominated by vast voids, regions where the density drops far below the average. The presence of these voids raises an important question. How does the universe maintain its structure despite being filled mostly with emptiness? To answer this, astronomers must consider not only where matter is present, but also where it isn't. Emptiness might seem like a simple absence, but in cosmic terms it plays a critical role in shaping the distribution of galaxies. The balance between filled and empty regions creates the environment in which the universe's structure evolves. The interaction between these regions reveals how sensitive the arrangement of galaxies is to even small differences in density. The large void near our position demonstrates how emptiness contributes to the fragile shape surrounding us. The cosmic web formed gradually as small fluctuations in the early universe grew under the influence of gravity. Slightly denser regions pulled in more matter. Slightly emptier regions shed matter toward the denser ones. Over billions of years, this process amplified the differences. Dense regions collected increasing amounts of mass, while the empty regions expanded and deepened. This early development laid the foundation for the structure we observe today. The voids grew larger. The filaments connecting dense regions became more pronounced. Clusters formed at the intersections. The overall pattern became more distinct with each passing era. The local void, sitting beside our galactic neighborhood, illustrates how emptiness participates in this ongoing transformation. Its low density allows the surrounding regions to pull matter away from its interior, widening the void's boundaries. This behavior influences the positioning of nearby galaxies. The local sheet, which contains the Milky Way and many of its closest neighbors, shows signs of this influence. The sheet's thin shape, its coherent motion, and its alignment all reflect the gravitational environment shaped partly by the void. Observing these features gives astronomers insight into how emptiness helps form the structures around us. The delicate nature of these structures becomes more evident when comparing galaxies in different environments. Galaxies in dense regions experience frequent interactions. They merge, collide, or pass close enough to disturb each other's shapes. Their evolution is rapid, influenced by the high density of their surroundings. In contrast, galaxies near voids experience far fewer encounters. Their evolution is quieter and steadier. This contrast provides a clear example of how environment shapes the behavior of galaxies. Differences in density, even minor ones, accumulate over billions of years to produce significant differences in galactic properties. The fragile shape of the cosmic web arises because gravitational forces respond to the distribution of mass with great sensitivity. A small accumulation of matter can grow into a filament. A slightly underdense region can develop into a void. The differences do not need to be dramatic initially. Gravity amplifies them over time. This amplification shows how the universe turns small variations into large structures. The local void likely began as a minor underdensity in the early universe. As matter flowed toward the denser regions nearby, the void gradually expanded. Its growth contributed to the shape of the local sheet by creating a region with reduced gravitational resistance on one side. Astronomers see similar behavior in other voids. Each void shapes its surroundings through the absence of mass. Galaxies at their edges move away. Filaments stretch around them. Sheets form between them. These processes show that emptiness isn't a passive backdrop. It is an active element in the universe's architecture. The fragile balance between emptiness and structure determines how galaxies move and how they gather. The universe's appearance today reflects billions of years of matter flowing along gravitational pathways shaped by both presence and absence. To understand how fragile the cosmic web is, one must consider the small degree of variation that existed in the early universe. The cosmic microwave background reveals temperature fluctuations on the order of 1 part in 100,000. These tiny variations correspond to small density differences that, over time, became the seeds of the cosmic web. Regions just slightly denser than average accumulated more matter. Regions slightly less dense gave up matter to their surroundings. The local void emerged from one of those slightly underdense beginnings. Its existence today reflects the universe's capacity to amplify minor differences into large-scale structure. The shape of the cosmic web is also influenced by the behavior of dark matter. Dark matter does not interact with light, but it exerts gravitational influence. It forms a scaffolding that guides the movement of normal matter. The distribution of dark matter determines where galaxies gather. In voids, the dark matter density is lower. As matter flows outward, the dark matter becomes more diffuse. This low density contributes to the expansion of voids. Meanwhile, dark matter collects more strongly in filaments and clusters. This redistribution reflects how sensitive the universe is to small differences in density. The fragile shape of the cosmic web depends on the behavior of dark matter just as much as on visible matter. Observations of the local void reveal how emptiness affects the motions of nearby galaxies. Galaxies at the edges show consistent outward drift. Their velocities indicate that the void has been growing for billions of years. This drift contributes to the shape of the surrounding structures. The local sheet's motion away from the void demonstrates that emptiness plays a direct role in shaping the flow of matter. The fragile balance of forces can be measured by comparing the motion of galaxies in different regions. Those near the void show weaker gravitational pulls from behind. Those facing dense regions show stronger pulls from ahead. This imbalance shapes the broader flow of galaxies. The fragility of this arrangement becomes clearer when examining simulations of cosmic structure formation. These simulations show that small changes in initial conditions can lead to noticeably different outcomes. A slightly different distribution of matter in the early universe could have altered the size or shape of the local void. It could have shifted the formation of the local sheet. It could have changed the orientation of the nearby filaments. This sensitivity demonstrates how easily the cosmic web could have developed differently. The actual structure that exists reflects one version of many possible outcomes, each shaped by the interplay of mass and emptiness. Even though the cosmic web looks robust on large scales, the details remain delicate. The boundaries between voids and filaments shift slowly over time. Galaxies drift along these boundaries, altering the shape little by little. Clusters grow by accreting matter from their surroundings. Filaments stretch and bend as gravity directs matter toward the densest intersections. The voids widen as galaxies leave them. Every part of the structure moves, none of it stays fixed. The overall pattern persists, but its details evolve continuously. This slow evolution reveals how dependent the structure is on the forces shaping it. The fragile shape of everything becomes even more apparent when considering the role of dark energy. Dark energy drives the accelerated expansion of the universe. This expansion affects the cosmic web by stretching the space between structures. Over time, distant regions drift farther apart. Voids grow larger, filaments lengthen. Clusters become more isolated. The boundaries between structures become more pronounced. This accelerated expansion subtly reshapes the cosmic landscape. adding another layer to the delicate balance that maintains the structure. As time passes, the expansion may eventually isolate the local group from more distant structures. The pull from the Great Attractor and Shapley may weaken as the universe expands, but the influence of the void will also change as the expansion accelerates. These long-term trends show that the structure we see today is only one stage in a much longer evolution. The fragile shape of the cosmic web continues to shift as the universe ages. Our position within this web reflects the balance of these forces. The Milky Way sits at the boundary of a significant void. This position influences its motion and the arrangement of its neighbours. The local sheet formed in part because of the void's presence. The galaxies within the sheet move together because they share the same gravitational environment. Their path reflects the dense regions ahead and the empty region behind. This arrangement creates a balanced setting where the collective motion reveals the underlying structure. Understanding the fragile shape of everything helps astronomers interpret many features of the universe. It clarifies why galaxies cluster where they do. It explains why voids grow as they do. It shows how matter flows across great distances. It helps identify the roles of dark matter and dark energy. And it demonstrates how small early differences grew into the structures observed today. The cosmic web's shape is not merely the result of matter gathering, it is also shaped by matter leaving. The presence of voids is just as important as the presence of filaments. The local void's influence extends across millions of light years. Its presence affects galaxy velocities, the arrangement of structures, and the shape of the nearby environment. The fragile balance between mass and emptiness determines how the local group moves and how the local sheet evolved. This balance holds the key to understanding our place in the cosmic landscape. When people look up at the night sky, it's easy to imagine that everything out there is evenly arranged, or that the galaxies drift through space without much structure guiding their paths. But the more astronomers study our surroundings, the clearer it becomes that the universe is shaped by contrasts. Some regions gather matter while others lose it. Some pull strongly while others remain mostly quiet. These contrasts shape the positions of galaxies, the motion of galaxy groups, and the arrangement of the vast cosmic web. And within this intricate landscape, our own position reveals something unexpected. We live right beside one of the universe's largest quiet zones, a region with so little matter that it influences everything near it simply by not being there. Understanding this position offers a different perspective on our galaxy and its surroundings. The Milky Way sits in a structure guided both by the presence of massive concentrations far ahead and by the emptiness located behind it. This emptiness, the nearby void, shapes the way our galaxy moves through space. It contributes to the overall flow of the local group. It influences the shape of the local sheet. It provides a boundary that marks the transition between where matter has gathered and where it has not. As astronomers trace these influences, they discover how strongly the distribution of emptiness defines the path our galaxy follows. The presence of emptiness might seem like an odd thing to focus on when thinking about cosmic structure, but the effects become more noticeable as measurements improve. The galaxies in our region move in a direction that lines up with the gravitational influence of the Great Attractor and the Shapley concentration. Their motion also aligns with the presence of the local void. The velocity of the local group, measured relative to the cosmic microwave background, contains a component shaped by this imbalance. The low-density region behind the local sheet reduces the gravitational pull from that direction. With less pull behind, the structures ahead exert more influence. The result is a motion that guides the local group steadily toward the mass-rich regions of the cosmic web. This motion reflects a deeper truth about our place in the universe. The large-scale structures around us behave as part of a complex network. The cosmic web connects clusters and filaments in patterns that span hundreds of millions of light years. The voids fill the spaces between these structures. Our galaxy occupies a location shaped by both. This position provides a blend of influences that reveal how the universe organizes itself. When astronomers trace the paths of galaxies across the local volume, they find that the motion of the local sheet matches what would be expected for a structure positioned at the edge of a major void. The sheet's shape, its thinness, and its direction of drift all align with this interpretation. The idea that we rest beside a quiet region of the universe is not new, but its significance has become clearer over time as measurements grew more precise. Early surveys hinted at the presence of an underdensity behind the Milky Way, but the limitations of telescopes and distance measurements made it difficult to confirm. As observations expanded into infrared and radio wavelengths, the map filled in. When the dust of the Milky Way could be seen through more effectively, the underdensity remained. Eventually, the data confirmed that the region was not simply a gap in observations, but a large void with very few galaxies. This void extends across a significant portion of the nearby universe and plays an important role in shaping the flow of matter along its boundaries. Resting beside this quiet region places the Milky Way in a dynamic setting. The galaxy's motion reflects the gravitational landscape. It drifts as part of the local group. The local group moves as part of the local sheet. The local sheet travels along a path shaped by both dense structures and empty regions. This layering of motion reveals how deeply interconnected the universe's structure is. Each layer reflects a different scale of influence. The smallest motions trace the interactions between nearby galaxies. The larger motions trace the drift of groups and sheets along the filaments of the cosmic web. The broadest motions reflect the pull of massive concentrations and the absence of pull from voids. Understanding these details offers a sense of how much emptiness contributes to the shape of the cosmic landscape. The local void is not the only feature that influences our region, but its role is significant. Without it, the local sheet would experience a different gravitational balance. The direction of motion might shift. The shape of the sheet might vary. The flow of galaxies within the local volume would change. Instead, the presence of the void ensures that the pull from ahead is not equally matched from behind. This imbalance helps determine the velocity of the local group and the broader motion of the structures around it. The quietness of the void also shapes nearby galaxies in other ways. Galaxies near voids often evolve differently from those in crowded environments. They experience fewer interactions and collisions. Their paths remain more stable. Their gas reservoirs can stay intact longer. Observing galaxies near the edges of voids allows astronomers to compare how different environments influence galactic evolution. The local void's proximity provides an opportunity to study these effects directly. The galaxies that sit near its boundaries show signs of outward motion as they drift away. Their velocities reveal the slow expansion of the void. Their properties reflect a quieter evolutionary history than galaxies in dense clusters. This gentle environment near the void adds another dimension to our understanding of how fragile the cosmic structure is. The balance between the gravitational pull from the dense regions and the lack of pull from the void shapes the pathways of galaxies. Even small differences in density can influence how structures form and evolve. The cosmic web emerges from these differences. The voids deepen, the filaments stretch, the sheets develop at the interfaces. This balance shows how sensitive the universe is to the distribution of matter and emptiness. As astronomers gather more observations, the shape of the nearby universe becomes clearer. They can map the distances to galaxies with increasing precision. They can determine the directions of their motions relative to the cosmic background. They can model the gravitational environment using both visible and dark matter. All of these tools help refine the understanding of our position. The picture that emerges is one of a galaxy group drifting gently along a path defined by the environment. The local void marks the quiet side. The Great Attractor and Shapley mark the dense side. Together, they shape the trajectory of the local group. This motion does not affect the daily experience of life within the Milky Way. The stars orbit the center of the galaxy. The planets follow their paths. But on the larger scales, the galaxy moves through space as part of the broader structure. The motion becomes part of a larger story about how galaxies travel along the filaments of the cosmic web. Our position near a void means that one of the dominant features shaping that motion is the absence of matter on one side. This absence allows the gravitational influence from the opposite direction to guide the local sheet more effectively. The quietness of the void also brings a sense of perspective about the nature of the universe. Even though voids contain few galaxies, they play a key role in defining the large-scale structure. They create boundaries. They allow filaments to form along their edges. They influence how galaxies arrange themselves. The local void serves as a reminder that structure is defined not only by what exists, but also by what does not. Emptiness shapes the universe in ways that become clear only by examining the motion of galaxies and the distribution of matter. The position of our galaxy near this quiet region invites a broader appreciation of how the universe organizes itself. The cosmic web stretches across unfathomable distances, but its structure depends on the same basic principles throughout. Regions with more mass attract matter. Regions with less mass let matter flow away. Over time, these flows create the pattern seen today. The local void, the local sheet, the nearby filaments, and the distant concentrations all reflect this interplay. Our place within this landscape is one instance of a pattern repeated across the universe. As time passes, the structures will continue to evolve. The void will keep expanding as galaxies drift farther away. The dense regions will draw in more matter, growing slowly over billions of years. The accelerating expansion of the universe will stretch the distances between structures. The motion we see today will continue, shaped by the same imbalance between the quiet void and the dense regions ahead. The path of the local group will persist, gradually carrying it along the same direction that has guided it for much of cosmic history. The quietness behind us offers a reminder of how much of the universe lies beyond direct experience. The Milky Way feels the pull of structures it cannot see with the naked eye. It responds to the absence of structures that appear empty even in deep surveys. It moves along paths carved out by gravitational influences stretching across millions of light years. The presence of the local void shapes the course of the galaxy without us noticing any change in daily life. Yet the influence is real and measurable. It becomes part of the ongoing story of how galaxies navigate the cosmic landscape. Resting beside this quiet region offers a stable view of the universe's behavior on the larger scales. The nearby emptiness provides a kind of gentle backdrop that influences everything around it. The motion of the local sheet remains coherent because of this environment. The alignment of nearby structures becomes clearer when the void is considered. The direction of the local group's drift becomes understandable as part of a broader pattern. This position does not isolate us from the rest of the universe. Instead, it connects us to the broader flow of matter through space. The galaxies move together along the filaments. The sheets form boundaries between voids. The clusters gather matter. Our galaxy participates in these processes, guided by both presence and absence. The quietness behind us becomes one of the defining elements of the environment shaping our path. As the narrative continues forward in scientific study, astronomers will keep refining models of the local universe. The growth of the void, the motion of the sheet, and the distribution of nearby structures will become clearer with improved measurements. Each new observation adds another detail to the picture of how galaxies move and how emptiness contributes to that motion. The quiet region beside us will continue to expand, shaping the long-term future of the nearby cosmic web. And so, our galaxy rests here, near one of the quietest parts of the universe, moving steadily through space along with its neighbours, shaped by the environment that surrounds it, following a path determined by both the mass-rich regions ahead and the deep stillness behind.